The universe, in all its vastness and complexity, is perhaps the most profound mystery we can contemplate as we drift into peaceful contemplation. Tonight, let us explore together the grand architecture of existence itself. The large-scale structure and composition of the cosmos that surrounds us, stretches beyond us, and connects us all. When we look up at the night sky, we see stars scattered across the darkness like diamonds on velvet. But this simple view barely hints at the true nature of the universe's structure. What we observe is only a tiny fraction of what exists, and even more intriguing, most of what makes up our universe is completely invisible to us. Let me share with you a remarkable fact that might seem almost impossible to believe. Of all the matter and energy in the entire universe, only about 5% is the ordinary matter that makes up everything we can see and touch. The stars, planets, galaxies, nebulae, you, me, the Earth beneath us, and everything we have ever observed directly. All of this accounts for merely 5% of the universe's total content. So what makes up the remaining 95%? This is where our journey into the cosmic unknown becomes truly fascinating. About 27% of the universe consists of something we call dark matter. Dark matter is one of the most mysterious substances in existence. We cannot see it, as it does not emit, absorb, or reflect light in any way we can detect. It is invisible to every telescope we have ever built, regardless of which part of the electromagnetic spectrum we use to search for it. Yet we know dark matter exists through its gravitational effects. When we observe how galaxies rotate, we find that they spin far too quickly for the amount of visible matter they contain. By all calculations based on the matter we can see, these galaxies should tear themselves apart. But they hold together, spinning gracefully through space, because there is additional mass we cannot see, holding them in a gravitational embrace. This invisible scaffolding is dark matter. Dark matter does not interact with ordinary matter in any way except through gravity. It passes through normal matter like a ghost through walls. Right now, as you rest comfortably, countless dark matter particles are streaming through your body, through the Earth, emerging on the other side without ever colliding with a single atom. It is everywhere, forming vast halos around galaxies, threading through the cosmos in immense filaments, yet remaining completely intangible to everything except the gentle pull of gravity. But even more mysterious than dark matter is the component that makes up the majority of our universe. About 68% of everything that exists is dark energy. If dark matter is mysterious, dark energy is profoundly enigmatic. Dark energy is not a substance or particle in any traditional sense. It appears to be a property of space itself. While gravity pulls everything together, dark energy pushes everything apart. It is the force driving the accelerating expansion of the universe. For most of the 20th century, astronomers believed the universe's expansion, which began with the Big Bang, was gradually slowing down due to gravity. This seemed logical. If you throw a ball into the air, gravity slows it down. Similarly, the gravitational attraction between all matter in the universe should slow its expansion. But in 1998, two independent teams of astronomers made a discovery that shocked the scientific world. They found that the universe's expansion is not slowing down at all. Instead, it is speeding up. Galaxies are moving away from each other at ever-increasing rates. Some force, which we now call dark energy, is pushing the universe to expand faster and faster. Imagine blowing up a balloon, but instead of you having to blow harder to make it expand faster, the balloon somehow inflates itself more vigorously over time, requiring less effort from you. That is what dark energy does to the fabric of space itself. The nature of dark energy remains one of the greatest puzzles in modern physics. We do not know what it is, where it comes from, or why it exists. We simply observe its effects and measure its presence. It permeates all of space uniformly, never clumping or clustering, always present at a constant density, even as space expands. As the universe grows larger, more dark energy comes into existence, filling the new space being created, continuing to accelerate the expansion in an endless feedback loop. So when we speak of the composition of the universe, we are really describing three components. 5% ordinary matter, the atoms and particles that make up everything familiar to us. 27% dark matter, the invisible gravitational scaffolding that holds structures together. And 68% dark energy, the mysterious force pushing space apart and accelerating the universe's expansion. Now let us turn our attention to the observable universe versus the entire universe, a distinction that opens up even deeper questions about the true scope of existence. The observable universe is the region of space from which light has had time to reach us since the beginning of the universe. The universe is approximately 13.8 billion years old. Light travels at a finite speed, about 300,000 kilometers per second, so there is a limit to how far we can see, based on how far light could have traveled in the time since the Big Bang. You might think this means the observable universe extends 13.8 billion light years in all directions, but the reality is more complex and beautiful, because space itself has been expanding during the time light has been traveling toward us. The observable universe actually extends about 46.5 billion light years in every direction from Earth. The total diameter of the observable universe is therefore about 93 billion light years. This is almost incomprehensibly vast. To put this in perspective, if we could shrink the Sun to the size of a white blood cell and shrink the Milky Way galaxy down using the same scale, the Milky Way would be approximately the size of the continental United States, and the observable universe would be more than 20 million times larger than that. There are an estimated 200 billion to 2 trillion galaxies in the observable universe, each containing hundreds of billions of stars. But here is where it becomes even more profound. The observable universe is not the entire universe. It is merely the part of the universe we can observe. Beyond the boundary of the observable universe, space continues. How far it continues, we do not know. It may be finite, curving back on itself in ways that are difficult to visualize, or it may be infinite, extending forever in all directions. Many cosmological models suggest the universe may indeed be infinite. If this is true, then beyond our observable bubble of 93 billion light years across, there is vastly more space, more galaxies, more stars, more planets. Everything we can see, every galaxy observed by every telescope, would represent an infinitesimally small fraction of what exists. In an infinite universe, every possible arrangement of matter that is consistent with the laws of physics would occur somewhere, not just once, but infinitely many times. There would be countless regions of space so far away that light from them will never reach us, each containing their own galaxies and stars, possibly their own observers looking up at their own skies, wondering about the nature of existence just as we do. The boundary of the observable universe is not a physical edge. It is simply a limit to what we can see, imposed by the finite age of the universe and the finite speed of light. This boundary is constantly expanding as more time passes, and light from more distant regions reaches us. Yet because space itself is expanding, and expanding at an accelerating rate due to dark energy, there are regions of space moving away from us faster than light can travel through space. Light from these regions will never reach us, no matter how long we wait. This means that as time passes, the observable universe grows, but paradoxically, some galaxies we can see today will eventually disappear from view. As dark energy continues to accelerate the universe's expansion, distant galaxies will cross a threshold beyond which their light can no longer reach us. Trillions of years in the future, observers in our galaxy will look out and see far fewer galaxies than we see today. Much of the universe will have receded beyond observation, slipping beyond the cosmic horizon forever. But let us return to the present and explore the magnificent structure that fills our observable universe, what astronomers call the cosmic web. If you could zoom out and view the universe on its largest scales, seeing the distribution of galaxies across billions of light years, you would observe one of nature's most beautiful patterns. Galaxies are not randomly scattered through space. Instead, they are organized into an intricate structure that resembles a three-dimensional spider's web spanning the entire cosmos. This cosmic web consists of 4 main components: galaxy clusters, filaments, walls, and voids. Galaxy clusters are the densest regions, where hundreds or even thousands of galaxies congregate together, bound by their mutual gravity. These clusters are among the largest gravitationally bound structures in the universe. The galaxies within them orbit around their common center of mass, held together despite the universe's overall expansion. The Virgo cluster, relatively nearby at about 50 million light-years away, contains approximately 1,500 galaxies. The Coma cluster, about 300 million light-years distant, contains more than 1,000 galaxies in a region only about 20 million light-years across. These galaxy clusters are not isolated. They are connected by filaments, vast thread-like structures of galaxies and dark matter stretching across hundreds of millions of light years. Filaments are the backbone of the cosmic web, the bridges linking one cluster to another. When we map the distribution of galaxies in 3 dimensions, these filaments appear as luminous pathways of matter threading through the darkness. Where multiple filaments intersect, we find galaxy walls or sheets, vast 2-dimensional surfaces covered with galaxies. The most famous example is the Sloan Great Wall, a cosmic structure containing billions of galaxies spread across 1 billion light years. These walls are relatively thin compared to their length and width, like cosmic membranes dividing space into cellular compartments. And then there are the voids. If the filaments and walls are where galaxies congregate, the voids are where they do not. Cosmic voids are immense empty regions of space containing very few galaxies. They are not completely empty, but they are far less dense than average. Some voids span hundreds of millions of light years across. The Boötes void, discovered in 1981, is approximately 330 million light years in diameter and contains only about 60 galaxies, far fewer than would normally occupy such a volume of space. These voids make up most of the volume of the universe, while galaxies are organized into dense filaments and clusters, accounting for only a small fraction of space. The voids occupy perhaps 80% of the universe's volume. We live in a universe that is mostly empty, with matter concentrated into cosmic threads and knots, surrounded by vast oceans of near emptiness. This cosmic web structure emerged from tiny density fluctuations in the early universe. Shortly after the Big Bang, the universe was remarkably uniform, but not perfectly so. There were tiny variations in density, regions that were very slightly more dense than average, and regions that were very slightly less dense than average. These variations were incredibly small, differing from the average by only about 1 part in 100,000, but gravity amplifies small differences. The slightly denser regions attracted more matter through gravity, becoming even denser. The slightly less dense regions lost matter to their denser neighbors, becoming even emptier. Over billions of years, this process transformed microscopic variations into the vast cosmic web we see today. Dark matter played a crucial role in this process. Because dark matter interacts only through gravity and not through electromagnetic forces, it could collapse and clump more efficiently than ordinary matter in the early universe. Dark matter formed the gravitational skeleton of the cosmic web first, and then ordinary matter fell into the gravitational wells created by dark matter, forming galaxies within the dark matter framework. Computer simulations of cosmic structure formation show this process with stunning clarity. Starting from the nearly uniform conditions of the early universe and applying the laws of gravity and the effects of dark energy, these simulations reproduce the cosmic web we observe, complete with filaments, clusters, and voids. The agreement between simulation and observation is one of the great successes of modern cosmology, confirming our understanding of how structure grows in an expanding universe dominated by dark matter and dark energy. Our own Milky Way galaxy is part of this cosmic web. We reside in a small galaxy cluster called the Local Group, which contains about 50 galaxies, including the Milky Way, the Andromeda Galaxy, and various smaller companions. The Local Group is itself part of a larger structure called the Laniakea Supercluster, a collection of galaxy clusters and groups spanning 500 million light-years and containing approximately 100,000 galaxies. Laniakea is not just a loose association of galaxies. The galaxies within it share a common motion, all flowing toward the same gravitational basin, a dense region called the Great Attractor. Despite the universe's overall expansion, on these local scales gravity still dominates, pulling galaxies together into coherent structures. We are, in a sense, floating along a filament of the cosmic web, carried by currents of dark matter toward a distant concentration of mass. The cosmic web is not static. It continues to evolve as the universe ages. Gravity pulls matter along filaments toward clusters, making the dense regions denser. Voids expand and empty further as matter drains away from them. In the distant future, if dark energy continues to dominate, this evolution will eventually cease. The accelerating expansion will overcome even the gravity-holding clusters together, pulling galaxies apart, dispersing the cosmic web, and isolating every galaxy in an ever-expanding ocean of space. But that future is trillions of years away. For now, the cosmic web remains a dynamic, evolving structure, a vast three-dimensional tapestry of matter and energy shaped by the invisible hand of gravity and the mysterious push of dark energy. Let us consider what this all means. We find ourselves in a universe that is far stranger and more complex than our ancestors could have imagined. Most of what exists is invisible and unknown to us. The universe is dominated by dark matter and dark energy, substances whose fundamental nature remains mysterious despite decades of research. We observe only a small fraction of a possibly infinite cosmos, a bubble of observable space surrounded by vastly more that we can never see. And within our observable universe, matter is arranged in a beautiful web-like pattern on the largest scales, with galaxies strung along filaments and concentrated in clusters, while vast voids lie between. This structure emerged from nearly imperceptible variations in the infant universe, amplified over billions of years by the action of gravity working on both ordinary and dark matter. We are part of this structure. Every atom in your body was forged in the heart of a star that lived and died before our sun was born. Those atoms were scattered into space in a supernova explosion, mixed with gas and dust in the cosmic web, and eventually gravitationally collapsed to form our solar system 4.6 billion years ago. We are, quite literally, made of stardust, organized by the same forces that shape the largest structures in the cosmos. The realization that we understand so little about the universe should not be cause for despair, but rather for wonder. Dark matter and dark energy remind us that the universe is full of mysteries waiting to be solved. The cosmic web shows us that even chaos follows patterns. That structure emerges from simplicity, given enough time and the right conditions. And the possibility that our observable universe is only a tiny part of a much larger, perhaps infinite cosmos, invites us to expand our perspective beyond even the grandest scales we can observe. We are observers in a vast experiment, witnesses to a universe unfolding according to laws we are gradually learning to understand. As you rest tonight, consider that you are floating on a planet orbiting a star in a galaxy flowing along a filament of the cosmic web, surrounded by mysterious dark matter and permeated by enigmatic dark energy, within a bubble of observable space that may be part of something infinitely larger. You are connected to the deepest structure of reality, a participant in the greatest story ever told, the story of the universe itself, this grand cosmic structure, from the smallest galaxies to the largest voids, from ordinary matter to dark energy. All of it exists in a delicate balance. The density of matter, the strength of dark energy, the rate of expansion. All these parameters fall within narrow ranges that allow complexity to exist. If the universe were slightly different in any number of ways, galaxies might never have formed, stars might never have ignited, planets might never have coalesced, life might never have emerged. Yet here we are, conscious observers capable of contemplating the very structure of existence. We can measure the expansion of space, map the distribution of galaxies, infer the presence of invisible matter, and detect the subtle acceleration caused by dark energy. We can reconstruct the history of the cosmos from its fiery beginning to its structured present, and we can project its evolution into a distant future. This ability to understand, to observe, to question and discover may be among the universe's most remarkable properties. In us, and perhaps in other observers elsewhere in the infinite expanse, the universe has become aware of itself. Through our observations and thoughts, the cosmos contemplates its own existence. The cosmic web continues to evolve tonight, as it has for billions of years, and will for billions more. Galaxies drift along their filaments, clusters grow more massive, voids expand further. Dark energy continues its inexorable work, stretching space itself, accelerating the universe toward a future that is cooler, darker, and more dispersed than today. But for now, in this moment, the universe retains its structure and beauty. The cosmic web spans the observable universe in an intricate pattern. Galaxies shine with the light of hundreds of billions of stars. Planets orbit those stars, some perhaps harboring life, others waiting silently in the dark. Dark matter provides the gravitational foundation for all of this, invisible but essential. And dark energy ensures that the cosmic story continues, that the universe remains dynamic, expanding, evolving into whatever future awaits. You are part of this magnificent tapestry, connected to everything from the smallest particle to the largest structure. From the beginning of time to its end, rest peacefully with this knowledge. You are a child of the cosmos, made of stardust, animated by energy that has flowed through the universe since its birth, contemplating existence from your small corner of an infinite whole. The universe is vast beyond comprehension, mysterious in its composition, beautiful in its structure, and you are here to witness it, to think about it, to be part of it. There is something profound and comforting in knowing our place in this grand design, in understanding that we are neither the center of everything nor separate from it, but rather participants in an ongoing cosmic adventure that began nearly 14 billion years ago and continues all around us, every moment of every day. How did the universe begin, and how is its fate determined? The question of how the universe began and how it will end represents humanity's deepest inquiry into the nature of existence itself. Tonight, as you rest comfortably, let us journey together through time, from the very first moment of creation to the distant future when the cosmos reaches its ultimate destiny. Our story begins with the Big Bang, though this name is somewhat misleading. There was no explosion in space. Rather, space itself came into existence, along with time, matter, and energy, in a singular event approximately 13.8 billion years ago. Before this moment, there was no before. Time itself began with the Big Bang. The very concepts of past and future, cause and effect, emerged alongside the universe itself. Imagine, if you can, that everything we observe today, every galaxy containing hundreds of billions of stars, every planet, every particle of matter and light, all of it was once compressed into a region smaller than a single atom. Not just the matter was compressed, but space itself. The entire observable universe, now 93 billion light years across, emerged from something incomprehensibly small and dense. In that first instant, the universe was unimaginably hot, far hotter than the core of any star. The temperature was approximately 10 to the power of 32 degrees, a number so large it defies intuitive understanding. At such extreme conditions, the fundamental forces we know today, gravity, electromagnetism, and the strong and weak nuclear forces, were unified into a single force. Matter as we know it could not exist. Even the basic particles like protons and electrons had not yet formed. But how do we know this happened? What evidence do we have for an event that occurred nearly 14 billion years ago, long before Earth existed, before the sun ignited, before our galaxy took shape? The evidence is both abundant and compelling, written in the very fabric of the cosmos itself. The first major piece of evidence is what we call cosmic redshift. In the 1920s, astronomer Edwin Hubble made a revolutionary discovery. He observed that nearly all galaxies are moving away from us, and more remarkably, the farther away a galaxy is, the faster it appears to be receding. This relationship, now called Hubble's law, revealed something profound about the universe itself. The light from distant galaxies is shifted toward the red end of the spectrum, stretched to longer wavelengths. This redshift occurs because space itself is expanding, carrying galaxies along with it like raisins in rising bread dough. As space expands, the light traveling through it gets stretched, increasing its wavelength and shifting it toward red. If all galaxies are moving apart from each other, then in the past, they must have been closer together. Running the cosmic movie backward, we can trace this expansion back to a time when all galaxies, all matter, all space itself, was concentrated in an infinitesimally small point. This realization gave birth to the Big Bang theory. But the most compelling evidence comes from something called the cosmic microwave background, often abbreviated as CMB. This is perhaps the most important discovery in all of cosmology, a window into the infant universe, a fossil of creation itself. The cosmic microwave background is a faint glow of radiation that fills the entire universe. It comes from every direction in space with nearly equal intensity. This radiation is not emitted by stars or galaxies, but rather it is the cooled remnant of the intense heat from the Big Bang itself. In the very early universe, everything was so hot and dense that matter existed as a plasma, a soup of charged particles where electrons were separated from atomic nuclei. Light could not travel freely through this plasma. It would be emitted and immediately absorbed again, trapped in an endless cycle of emission and absorption. The universe was opaque, like being inside a thick fog. But as the universe expanded, it cooled. About 380,000 years after the Big Bang, the temperature dropped enough for electrons and nuclei to combine and form the first neutral atoms, mostly hydrogen and helium. At this moment, light was suddenly free to travel through space unimpeded. The fog cleared, and the universe became transparent for the first time. The light released at that moment has been traveling through space ever since. But because space has been expanding, the wavelength of this light has been stretched tremendously. What started as visible light, glowing at a temperature of about 3,000 degrees, has been stretched into microwaves, corresponding to a temperature of just 2.7 degrees above absolute zero. This cosmic microwave background was predicted by the Big Bang Theory and discovered accidentally in 1964 by two radio astronomers, Arno Penzias and Robert Wilson. They detected a persistent background noise in their antenna that came from all directions and would not go away. What they had found, though they did not initially realize it, was the echo of creation itself, the oldest light in the universe. Modern satellites have mapped the cosmic microwave background with exquisite precision. These maps reveal tiny temperature variations across the sky, fluctuations of only a few millionths of a degree. These variations correspond to slight density differences in the early universe, the seeds from which all structure, galaxies, stars, planets, emerged through gravitational attraction over billions of years. The cosmic microwave background provides a snapshot of the universe when it was only 380,000 years old, a baby by cosmic standards. It confirms the Big Bang Theory's predictions with remarkable accuracy, showing us that the universe was indeed once much hotter, denser, and more uniform than it is today. Another line of evidence comes from the abundance of light elements in the universe. The Big Bang Theory predicts that in the first few minutes after creation, the universe was hot enough for nuclear fusion to occur, creating the lightest elements from primordial protons and neutrons. Specifically, the theory predicts that about 75% of ordinary matter should be hydrogen and about 25% helium, with trace amounts of deuterium, lithium, and other light elements. When we observe the universe, we find exactly these proportions. The agreement between prediction and observation is so precise that it provides powerful confirmation of the Big Bang Theory. The hydrogen and helium we observe were forged in the first 3 minutes of cosmic history. But our story does not end with the Big Bang itself. In fact, the very earliest moments of the universe's existence involve a remarkable period called cosmic inflation. According to our best models, the universe underwent a period of extraordinarily rapid expansion in the first tiny fraction of a second after the Big Bang, between approximately 10 to the power of negative 36 seconds and 10 to the power of negative 32 seconds after the beginning. The universe expanded by a factor of at least 10 to the power of 26. Space itself inflated faster than the speed of light. This may seem to violate Einstein's principle that nothing can travel faster than light, but it does not. Objects moving through space cannot exceed light speed, but space itself can expand at any rate. During inflation, space expanded so rapidly that regions which started in contact were suddenly separated by vast distances, far too large for light to have crossed in the available time. Cosmic inflation solves several puzzles about the universe. First, it explains why the universe appears so uniform in all directions. Different regions of space that we observe today were once in close contact during the pre-inflation era, allowing them to reach the same temperature and density. Inflation then stretched these uniform regions to cosmic scales. Second, inflation explains why the universe appears spatially flat. Just as inflating a balloon makes its surface appear flatter and flatter, the tremendous expansion during inflation smoothed out any curvature that space might have had initially. Third, and perhaps most remarkably, inflation provides a mechanism for generating the tiny density fluctuations we observe in the cosmic microwave background. Quantum fluctuations at subatomic scales were stretched to cosmic proportions during inflation, becoming the seeds of all structure in the universe. The galaxies, clusters, and cosmic web we observe today all originated from quantum uncertainty in the first fraction of a second of existence. The evidence for inflation is circumstantial but compelling. The patterns we observe in the cosmic microwave background match the predictions of inflationary theory with impressive precision. The universe's flatness, uniformity, and structure all point to this brief period of exponential expansion in its earliest moments. After inflation ended, the universe continued to expand, but at a much more sedate pace. It remained extremely hot for the first few minutes, gradually cooling as space expanded. During this time, as we mentioned, nuclear fusion created the first light elements, Then came a long period astronomers call the Cosmic Dark Ages, lasting several 100 million years, when the universe was filled with neutral gas but contained no stars or galaxies to illuminate it. Eventually, gravity caused the densest regions to collapse, forming the first stars. These early stars were massive, burning bright and hot, living fast and dying young in spectacular supernova explosions. Their radiation began to ionize the hydrogen gas filling space, and their deaths scattered heavier elements into the cosmos. From these enriched materials, new generations of stars formed, along with the first galaxies. Over billions of years, galaxies merged and grew, forming the cosmic web structure we observe today. Stars lived and died in countless cycles, gradually building up the inventory of heavy elements necessary for planets and eventually life. Our own solar system formed 4.6 billion years ago from gas and dust enriched by previous generations of stars. Life emerged on Earth, evolved, and eventually gave rise to conscious observers capable of contemplating the universe's origin. This brings us from the universe's beginning to our present moment. But what of the future? How will the cosmic story end? This question has occupied cosmologists for decades, and the answer depends critically on the universe's composition and the behavior of dark energy. There are three main possibilities for the universe's ultimate fate, each dramatically different, each depending on different assumptions about cosmic physics. The first possibility is called the Big Crunch. In this scenario, the universe's expansion eventually slows, stops, and reverses. Gravity, pulling everything together, ultimately overcomes the expansion. Galaxies begin moving toward each other rather than apart. Over billions of years, the universe contracts, growing denser and hotter, until all matter and energy collapse back into a singularity similar to the one from which the Big Bang emerged. The Big Crunch would be like watching the history of the universe in reverse. The cosmic web would compress, galaxies would merge together, stars would become closer and closer. Eventually, space itself would shrink to nothing, and time, as we understand it, would end. Some theories suggest this could lead to a cyclical universe, where each Big Crunch is followed by a new Big Bang, creating an eternal cycle of expansion and contraction. For the Big Crunch to occur, the universe would need to be denser than a critical value, with enough matter and energy that gravity can overcome the expansion. However, observations have shown that our universe does not contain sufficient matter for this scenario. Unless dark energy behaves very differently than we currently observe, the Big Crunch appears unlikely. The second possibility, and currently the most probable based on observations, is called heat death, or sometimes the Big Freeze. In this scenario, the universe continues expanding forever. Dark energy continues to accelerate this expansion, driving galaxies farther and farther apart. Over time, the universe grows increasingly cold, dark, and empty. Let me walk you through the stages of this long cosmic decline, though the timescales involved are almost impossible to comprehend. In about 4 billion years, our Milky Way galaxy will collide and merge with the Andromeda Galaxy. This will create a new, larger galaxy, sometimes called Milkomeda. Such galaxy mergers will continue for some time, but eventually, dark energy will win. Galaxies beyond our local group will recede beyond the cosmic horizon, their light redshifted to invisibility. Observers in the distant future will see far fewer galaxies than we see today. After about 1 trillion years, star formation will cease throughout the universe. The gas and dust needed to make new stars will be exhausted. All existing stars will gradually burn out. The smallest, most efficient stars, the red dwarfs, can burn for trillions of years, but even they will eventually exhaust their fuel. The universe will grow dark as the last stars fade. After 10 to the power of 40 years, even the longest-lived stellar remnants, white dwarfs and neutron stars, will have cooled to the temperature of space itself, becoming black dwarfs, dark and cold. Galaxies, now just collections of dead stars and stellar remnants, will gradually evaporate as stars are ejected through gravitational interactions. Black holes will be the last major structures to persist. They grow through accretion and mergers, but even black holes are not eternal. Through a quantum process called Hawking radiation, black holes slowly evaporate, losing mass over immense periods of time. The rate of evaporation is inversely related to mass, so larger black holes take longer to disappear. A black hole with the mass of our Sun would take 10 to the power of 67 years to evaporate completely. Supermassive black holes at the centers of galaxies, billions of times more massive than the Sun, would persist for 10 to the power of 100 years or longer. But eventually, even they will vanish in a final burst of radiation, leaving nothing behind. After 10 to the power of 100 years, or perhaps much longer, the universe will contain only a thin soup of elementary particles, photons, neutrinos, and electrons spread across space that continues to expand. The temperature will be infinitesimally close to absolute zero. No structures will exist, no stars will shine, no processes will generate heat or light. The universe will have reached maximum entropy, a state of total disorder where no energy gradients exist to drive any process. This is heat death, not death by excessive heat, but death characterized by the complete absence of usable energy. The universe will persist in this state forever, expanding, cooling, becoming ever more diffuse and empty, with no possibility of change or complexity. It is a future of eternal darkness and cold. The heat death scenario is currently considered most likely based on observations of dark energy and the universe's accelerating expansion. However, there is a third possibility, more speculative but terrifying in its implications, called the Big Rip. The Big Rip scenario depends on the nature of dark energy. Currently, dark energy appears to have constant density, meaning as space expands, more dark energy comes into existence, maintaining the same energy per unit volume. This leads to the heat death scenario. But what if dark energy's density increases over time? Some theoretical models suggest dark energy might become stronger as the universe ages, a phenomenon called phantom energy. If this is true, dark energy would not only accelerate the universe's expansion, but would accelerate the acceleration itself, causing expansion to increase exponentially over time. In the Big Rip scenario, this accelerating expansion eventually becomes so extreme that it overcomes all forces, even those binding matter together at the smallest scales. First, galaxy clusters are torn apart as dark energy overcomes the gravity holding them together. Then individual galaxies are shredded. Then solar systems are disrupted, with planets torn from their orbits around stars. As the expansion continues to accelerate, stars themselves are torn apart, despite the tremendous gravitational pressure holding them together. Eventually, planets disintegrate. Molecules are ripped apart into individual atoms. Atoms themselves are torn to pieces, with electrons stripped from nuclei. Finally, even atomic nuclei, bound by the strongest force in nature, are torn apart into individual protons and neutrons. In the final moments, even protons and neutrons might be shredded into their constituent quarks. The Big Rip would occur at a specific moment in the finite future, unlike heat death, which approaches gradually. Everything in the universe would be torn apart simultaneously when the expansion rate becomes infinite. Time and space themselves might end in this scenario, much like in the Big Crunch, but reach through expansion rather than contraction. Current observations suggest the Big Rip is unlikely. The behavior of dark energy we observe is consistent with constant density, not increasing density. However, we cannot completely rule it out. Dark energy is so poorly understood that we cannot predict with certainty how it will behave over cosmic timescales. Each of these three possibilities represents a different answer to the ultimate question of cosmic destiny, yet all share certain features. In every scenario, the universe as we know it is temporary. The era of stars and galaxies, of life and complexity, is a brief chapter in cosmic history, already 14 billion years old, but perhaps only trillions of years remaining before it ends. We live in a special time, cosmically speaking. The universe is old enough to have formed complex structures, galaxies, stars, planets, and life, yet young enough that stars still shine and energy is available to drive interesting processes. In the far future, regardless of which scenario unfolds, the universe will be a vastly different place, likely inhospitable to any form of complexity or life as we understand it. Yet there is profound beauty in this understanding. We are here, now in this special epoch of cosmic history, able to observe and understand the universe. We can trace its history from the first fraction of a second to the present day. We can map its structure across billions of light years. we can peer into its distant future and contemplate its ultimate fate. The Big Bang Theory, supported by multiple independent lines of evidence, tells us that everything we observe emerged from an incredibly hot, dense state nearly 14 billion years ago. Cosmic inflation explains how quantum fluctuations in the first moments of existence became the seeds of all structure. The cosmic microwave background shows us the universe as it was when it was just 380,000 years old, confirming our models with remarkable precision. And looking forward, the accelerating expansion driven by dark energy suggests the universe will continue growing, cooling, and darkening until it reaches a state of maximum entropy, a heat death where nothing can ever change again. This may seem like a bleak ending, but it is many trillions of years away, an almost incomprehensible span of time during which countless possibilities may unfold. Consider that the universe existed for 9 billion years before our solar system formed. Earth existed for several billion years before complex life evolved. Humanity has existed for only a tiny fraction of Earth's history, and our technological civilization for less than the blink of an eye in cosmic terms. Who can say what may emerge in the immense expanse of time before the stars burn out? Perhaps other civilizations will arise, more advanced than we can imagine, finding ways to preserve complexity and meaning even as the universe ages. Perhaps consciousness itself will evolve into forms we cannot conceive, finding purpose in the darkening cosmos. Or perhaps life is a brief spark in an uncaring universe, precious because it is temporary, meaningful because it is rare. The story of the universe, from its explosive beginning to its gradual ending, is ultimately a story of change. Nothing remains constant. The universe that existed 1 second after the Big Bang bore no resemblance to what we see today. The universe of the far future will be equally different, perhaps stranger than we can imagine. We are part of this cosmic story, made of atoms forged in stars that died billions of years ago, assembled through processes driven by the fundamental forces and the expansion of space itself. We exist in this narrow window of cosmic time when the universe is complex, dynamic, and capable of supporting structures like stars, planets, and life. There is something humbling yet also empowering in this knowledge. We are tiny, insignificant, on cosmic scales, yet we are capable of understanding the universe's grandest scales and deepest history. In contemplating the Big Bang and cosmic inflation, we reach back to the very first moments of existence. In considering heat death or the Big Rip, we peer forward to the ultimate fate of everything that is. Tonight, as you rest, remember that you are part of this grand cosmic narrative. You exist because the universe began in a hot, dense state and has been expanding and evolving for nearly 14 billion years. The atoms in your body pass through multiple generations of stars. The energy in your cells ultimately derives from sunlight powered by nuclear fusion in our star's core, a process created in the first minutes after the Big Bang. You are connected to both the beginning and the end, a momentary pattern of organized complexity in a universe slowly sliding toward disorder, a brief awakening of matter capable of reflecting on its own existence. Rest peacefully in this knowledge, knowing that you are part of something vast and ancient, something beautiful and temporary, something mysterious yet increasingly understood. The universe began in fire and will likely end in ice. But between these extremes lies everything we know, everything we are, everything we might become. That middle chapter, the one we inhabit now, is perhaps the most remarkable of all, for it is the time when the universe becomes aware of itself, when matter arranges itself in ways complex enough to ask questions, seek answers, and find meaning in the grand cosmic story. What are the most extreme and energetic objects in the cosmos? The universe is filled with objects so extreme they challenge the very limits of physics and human imagination. Tonight, as you drift into peaceful rest, let us explore these cosmic extremes together, the most powerful, dense, and energetic phenomena that exist anywhere in space and time. We begin our journey with perhaps the most mysterious and fascinating objects in all of existence, Black holes. Black holes represent the ultimate victory of gravity over all other forces. They are regions of space-time where gravity has become so intense that nothing, not even light itself, can escape. The very name evokes mystery and perhaps a touch of fear, but black holes are not cosmic vacuum cleaners randomly destroying everything around them. They are instead natural consequences of Einstein's theory of general relativity, objects whose existence was predicted by mathematics decades before we found evidence they truly exist. To understand black holes, we must first understand how they form. The most common type of black hole, called a stellar mass black hole, is born from the death of a massive star. Throughout its life, a star maintains a delicate balance. Gravity pulls inward, trying to collapse the star, while the outward pressure from nuclear fusion in the star's core pushes back, supporting the star against its own weight. But nuclear fusion requires fuel, and eventually, even the most massive stars exhaust their supply. When a star at least 20 times more massive than our Sun runs out of fuel, catastrophe strikes. Without the outward pressure from fusion, there is nothing to hold the star up against gravity's relentless pull. The core collapses suddenly and violently. In less than a second, the core of the star, a region about the size of Earth containing more mass than our Sun, collapses to a point. The outer layers of the star, suddenly finding nothing beneath them to hold them up, fall inward at speeds approaching 1/4 the speed of light. When this infalling matter rebounds off the collapsed core, it creates a supernova explosion, one of the most violent events in the universe, briefly outshining an entire galaxy. But at the center, where the core collapsed, something remarkable remains. If the core's mass exceeds about 3 times the mass of the Sun, nothing in the known universe can prevent complete gravitational collapse. The core continues shrinking past the size of a neutron star, past any size describable by ordinary physics, becoming a black hole. The anatomy of a black hole is both simple and profound. At the center lies the singularity, a point of infinite density where all the black hole's mass is concentrated. Here, the curvature of space-time becomes infinite and our mathematical descriptions of physics break down completely. We simply do not know what happens at the singularity. It represents the boundary of our understanding, a place where general relativity and quantum mechanics, our two great theories of physics, both apply yet contradict each other. Surrounding the singularity is the event horizon, the defining feature of a black hole. The event horizon is not a physical surface, but rather a boundary in space-time, the point of no return. Any object that crosses the event horizon is doomed to reach the singularity. No force in the universe can prevent this fate. Even light, traveling at the cosmic speed limit, cannot escape once it crosses this boundary, which is why we call these objects black holes. The size of the event horizon depends on the black hole's mass. For a black hole with the mass of our Sun, the event horizon would have a radius of about 3 kilometers. For a black hole 10 times more massive, the radius would be 30 kilometers. Despite containing more mass than entire stars, stellar mass black holes are remarkably compact objects. From the outside, if you could observe a black hole from a safe distance, you would see something strange and beautiful. The black hole itself would appear as a perfect sphere of absolute darkness. The event horizon, surrounded by a thin ring of light. This light comes from material falling toward the black hole, heated to millions of degrees by friction and compression, glowing brilliantly just before crossing the event horizon and vanishing forever. But black holes do not just swallow everything nearby. An object in a stable orbit around a black hole is no more in danger than a planet orbiting a star. If our Sun were suddenly replaced by a black hole of the same mass, Earth would continue orbiting exactly as before. We would freeze without the Sun's heat and light, but we would not be pulled into the black hole. Black holes are dangerous only to objects that venture very close to them. Strange things happen near black holes, consequences of Einstein's general relativity. Time itself flows differently in strong gravitational fields. If you could watch someone fall toward a black hole from your safe vantage point far away, you would see them move more and more slowly as they approach the event horizon. Their clock would appear to tick more slowly. Their movements would seem to slow down, and the light from them would redshift, becoming dimmer and redder. You would never actually see them cross the event horizon. They would appear frozen at the boundary, asymptotically approaching it, but never quite reaching it. eventually fading from view as their light became too redshifted to detect. But from the perspective of the person falling, something very different happens. They would cross the event horizon in a finite amount of time, experiencing nothing particularly special at the moment of crossing. The event horizon is not a physical barrier they could detect locally. Only after crossing would they realize their fate is sealed. Ahead lies only the singularity, and no force can prevent them from reaching it, typically in a fraction of a second for a stellar mass black hole. As they fell toward the singularity, they would experience tidal forces, the difference in gravitational pull between their head and their feet, or between their left side and their right side. Near the singularity of a stellar mass black hole, these tidal forces would become extreme, stretching and compressing the unfortunate traveler in a process astronomers sometimes call spaghettification. Long before reaching the singularity, they would be torn apart by these tidal forces. Stellar mass black holes, formed from collapsed stars, typically have masses between about 3 and several dozen times the mass of our Sun. But the universe contains black holes far more massive and mysterious. Supermassive black holes. At the center of nearly every large galaxy, including our own Milky Way, lurks a supermassive black hole with a mass millions or even billions of times that of our Sun. The supermassive black hole at the center of our galaxy, called Sagittarius A star, has a mass of about 4 million times our Sun's mass. The largest supermassive black holes we have discovered exceed 10 billion solar masses, containing more mass than some entire galaxies. The origin of supermassive black holes remains one of astronomy's great mysteries. They cannot form from stellar collapse, as that produces only stellar mass black holes. Instead, supermassive black holes probably grew over billions of years, starting from smaller seed black holes in the early universe and growing through accretion of gas and mergers with other black holes. Some may have formed directly from the collapse of massive clouds of gas in the early universe, bypassing the stellar stage entirely. Despite their enormous mass, supermassive black holes have much larger event horizons than their stellar mass cousins. The event horizon of a billion solar mass black hole extends about 6 billion kilometers from the center, roughly the size of our solar system. This large size has an interesting consequence. The tidal forces at the event horizon of a supermassive black hole are relatively mild. You could cross the event horizon of a large enough supermassive black hole without immediately being torn apart, though your fate would still be sealed, with the singularity inevitable in your future. Supermassive black holes play a crucial role in galaxy evolution. The black hole at a galaxy's center and the galaxy itself appear to grow together, influencing each other's development. When gas falls toward a supermassive black hole, it forms an accretion disk, a swirling vortex of material spiraling inward. Friction within the disk heats the gas to millions of degrees, causing it to emit tremendous amounts of radiation across the electromagnetic spectrum. This can make the galactic center incredibly luminous, sometimes outshining all the stars in the galaxy. Combined, the energy released by material falling into supermassive black holes can also drive powerful jets of particles and radiation perpendicular to the accretion disk, shooting out at nearly the speed of light and extending for hundreds of thousands or even millions of light years into space. These jets can affect the entire galaxy, heating gas clouds, regulating star formation, and shaping the galaxy's evolution. In 2019, astronomers achieved something remarkable. Using a network of radio telescopes spanning the Earth, they captured the first direct image of a black hole's event horizon. The target was the supermassive black hole at the center of the galaxy Messier 87, about 55 million light-years away, with a mass 6.5 billion times our Sun. The image showed exactly what theory predicted: a dark, circular region, the shadow of the event horizon, surrounded by a bright ring of glowing gas. It was direct visual confirmation of black holes' existence, and a triumph of theoretical physics. But black holes are not the only extreme objects in the cosmos. Let us turn our attention now to neutron stars, objects that rival black holes in their remarkable properties. Neutron stars are what remain when massive stars explode as supernovas, but the core is not quite massive enough to collapse completely into a black hole. If the stellar core has a mass between about 1.4 and 3 times the Sun's mass, the collapse is halted not by ordinary atomic forces, but by a quantum mechanical effect called neutron degeneracy pressure. When the core collapses, it becomes so dense that protons and electrons are squeezed together, combining to form neutrons. What emerges is a sphere made almost entirely of neutrons, packed together as tightly as matter can be packed without collapsing into a black hole. A neutron star is essentially a gigantic atomic nucleus, about 20 kilometers in diameter, but containing more mass than our entire sun. The density of a neutron star defies comprehension. A single teaspoon of neutron star material would have a mass of about 1 billion tons, equivalent to the mass of a mountain compressed into a volume smaller than a sugar cube. If you could somehow place this teaspoon of neutron star material on Earth, it would instantly sink through the ground, through the Earth's crust, mantle and core, and emerge on the other side, oscillating back and forth through the planet like a pendulum. Neutron stars possess the strongest magnetic fields known in the universe, trillions of times stronger than any magnetic field we can create in laboratories or find anywhere else in nature. They also spin incredibly rapidly, a consequence of conservation of angular momentum during the core collapse. When a slowly rotating star collapses to a tiny fraction of its original size, it spins faster, like a figure skater pulling in their arms. Some neutron stars rotate hundreds of times per second. The fastest known pulsar, designated PSR-J 1748-2446 AD, spins 716 times every second. This means a point on its equator is moving at about 1/4 the speed of light. Despite this incredible rotation, the neutron star remains intact, held together by its enormous gravity. Many neutron stars appear to us as pulsars, one of the most precisely periodic phenomena in nature. Pulsars emit beams of radiation from their magnetic poles like cosmic lighthouses. As the neutron star rotates, these beams sweep across space. If Earth happens to lie in the path of a beam, we detect a pulse of radiation each time the beam sweeps past us. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell, then a graduate student who noticed incredibly regular pulses of radio waves coming from a fixed point in the sky. The pulses arrived with such precise timing that the research team briefly considered whether they might be signals from an extraterrestrial civilization, even jokingly referring to the source as LGM-1 for Little Green Men 1. However, they soon found more pulsars and realized these were natural phenomena, rapidly rotating neutron stars. The regularity of pulsar pulses is extraordinary. The most stable pulsars keep time as accurately as atomic clocks. Millisecond pulsars, which rotate hundreds of times per second, are among the most precise clocks in the universe. Their timing is so stable that networks of pulsars could potentially be used to detect gravitational waves, ripples in space-time itself passing through our region of the galaxy. Neutron stars in binary systems, orbiting another star or another neutron star, can accrete matter from their companion. This infalling matter can cause the neutron star to emit intense X-rays, making these systems among the brightest X-ray sources in the sky. In some cases, the accretion can cause the neutron star to spin faster, transforming it into a millisecond pulsar. When two neutron stars orbit each other, they gradually spiral inward, losing energy to gravitational waves. Eventually, after billions of years of slowly approaching each other, they collide and merge. This collision produces a brief but incredibly intense burst of gravitational waves and electromagnetic radiation across the spectrum. The merger likely forms a black hole, but in the process, it also creates heavy elements like gold and platinum through rapid nuclear reactions, scattering these precious metals into space. In 2017, astronomers detected gravitational waves from a neutron star merger for the first time, an event that occurred 130 million light-years away. Within seconds, telescopes around the world turned toward the source and observed the fading glow of the collision across multiple wavelengths. This observation confirmed that neutron star mergers are indeed a major source of heavy elements in the universe. Some neutron stars, called magnetars, possess magnetic fields even stronger than typical neutron stars, up to 1,000 times more intense. These are the strongest magnetic fields in the known universe. A magnetar's magnetic field is so intense that it distorts the atoms in the neutron star's crust, causing starquakes that release bursts of X-rays and gamma rays. At a distance of just 1,000 kilometers from a magnetar, its magnetic field would be strong enough to disrupt the molecular bonds in your body. Even at a distance of 1,000 kilometers from Earth, a magnetar's magnetic field could erase every magnetic stripe on every credit card on the planet. But even neutron stars and black holes are not the most luminous objects in the universe. That distinction belongs to quasars, objects so bright they can outshine 1 trillion stars. Quasars are among the most distant objects we can observe, most of them billions of light years away. When we observe a quasar, we are looking back in time, seeing the universe as it was billions of years ago. The name quasar comes from quasi-stellar radio source, because when they were first discovered in the 1960s, they appeared as point-like sources of light similar to stars, but with unusual properties. We now understand that quasars are supermassive black holes in the centers of distant galaxies, actively consuming vast amounts of material. The black holes powering quasars can have masses billions of times greater than our Sun, and they are surrounded by accretion disks containing gas spiraling inward at tremendous speeds. The accretion disk around a quasar's black hole is heated to millions of degrees by friction, causing it to emit enormous amounts of radiation across the electromagnetic spectrum. A single quasar can be more than 1,000 times brighter than an entire galaxy containing hundreds of billions of stars. The most luminous quasars can be seen from distances exceeding 13 billion light-years, meaning we observe them as they were when the universe was less than 1 billion years old. The power output of a quasar is almost incomprehensible. A typical quasar releases more energy every second than 10 trillion stars like our Sun. Some quasars emit the equivalent energy of converting millions of Earth masses into pure energy every year. This energy comes from the conversion of gravitational potential energy to radiation as matter falls toward the black hole. It is the most efficient power source in the universe, converting up to 40% of infalling matter's mass directly into energy, far more efficient than nuclear fusion in stars, which converts less than 1% of mass to energy. Many quasars also produce relativistic jets, streams of particles accelerated to nearly the speed of light, shooting away from the black hole perpendicular to the accretion disk. These jets can extend for millions of light years, far beyond the galaxy hosting the quasar. When one of these jets happens to point directly at Earth, we see an especially bright quasar called a blazar, and the radiation we detect can be boosted by relativistic effects. Quasars were much more common in the early universe than they are today. In the present era, most supermassive black holes, including the one at the center of our Milky Way, are relatively quiet, not actively consuming large amounts of material. But in the early universe, when galaxies were younger and gas was more abundant, many supermassive black holes were actively accreting, shining as brilliant quasars. The study of quasars tells us about the early universe and the formation of the first galaxies and supermassive black holes. The most distant quasars we observe existed when the universe was less than 1 billion years old, yet they already contain black holes with billions of solar masses. How these enormous black holes formed so quickly remains an active area of research and one of the mysteries of modern cosmology. But if quasars are the most luminous sustained sources in the universe, gamma-ray bursts are the most luminous transient events, brief flashes of energy that represent the most explosive phenomena since the Big Bang itself. Gamma-ray bursts, often abbreviated as GRBs, are exactly what they sound like: intense bursts of gamma rays, the most energetic form of electromagnetic radiation. They were discovered accidentally in the 1960s by satellites designed to detect nuclear weapons tests. These satellites detected brief, intense flashes of gamma rays coming from space, and it took decades to understand what was causing them. We now know there are two types of gamma ray bursts, distinguished by their duration. Short gamma ray bursts, lasting less than 2 seconds, are produced by the merger of two neutron stars, or a neutron star and a black hole. Long gamma ray bursts, lasting from a few seconds to several minutes, are produced by the collapse of extremely massive stars, more than 30 times the Sun's mass, in a type of supernova called a hypernova or collapsar. A gamma-ray burst releases as much energy in a few seconds as our Sun will emit over its entire 10 billion year lifetime. The most energetic gamma-ray bursts release more energy in 10 seconds than our Sun will produce in its entire existence, repeated 10 billion times over. If you could somehow convert the entire mass of our Sun directly into pure energy in an instant, it would roughly equal the energy output of a powerful gamma-ray burst. This incredible energy is concentrated into two narrow beams, jets of material and radiation shooting out in opposite directions at 99.99% the speed of light. The gamma rays we detect from a gamma-ray burst come from one of these jets pointed toward Earth. Because the jet is moving at nearly the speed of light directly toward us, relativistic effects amplify the radiation we observe, making the burst appear even more energetic. When a gamma-ray burst occurs, it briefly becomes the brightest object in the gamma-ray sky, despite often being billions of light years away. If a gamma-ray burst occurred in our galaxy and its jet pointed directly at Earth, the consequences could be severe. The burst of gamma rays could damage our ozone layer, exposing the surface to harmful solar ultraviolet radiation. Some scientists have speculated that a gamma ray burst might have been responsible for one of Earth's mass extinction events hundreds of millions of years ago, though this remains hypothetical. Fortunately, gamma ray bursts are rare in any given galaxy, occurring perhaps once every few 100,000 or million years. The orientation of the jet matters as well. Only if the jet points toward us do we detect the full intensity of the burst. Most gamma-ray bursts in the universe go undetected because their jets point in other directions. The afterglow of a gamma-ray burst can be detected in X-rays, visible light and radio waves for days, weeks, or even months after the initial burst. This afterglow occurs as the relativistic jet plows through surrounding material, creating a shockwave that heats gas and produces radiation. By studying this afterglow, astronomers can determine the gamma ray burst's distance and learn about the environment surrounding the explosion. The most distant gamma ray burst ever detected occurred more than 13 billion light years away, meaning it happened when the universe was only about 600 million years old. These distant bursts provide information about the early universe, including the formation of the first stars and galaxies. Some gamma-ray bursts have been associated with supernova explosions, confirming that long-duration bursts come from the deaths of massive stars. The gamma-ray burst and supernova occur nearly simultaneously, the burst representing the initial collapse and jet formation, while the supernova is the explosion of the star's outer layers. In recent years, astronomers have detected electromagnetic signals accompanying the gravitational waves from neutron star mergers, providing direct confirmation that these mergers produce short gamma-ray bursts. This was one of the most exciting discoveries in modern astronomy, directly linking two of the universe's most extreme events. Black holes, neutron stars, quasars, and gamma-ray bursts represent the universe at its most extreme. They push the boundaries of physics, creating conditions of density, energy, and gravity that cannot be replicated anywhere else. They challenge our understanding and force us to apply our theories in regimes far beyond everyday experience. These objects remind us that the universe is far more dynamic and energetic than the night sky might suggest. Out there, beyond the peaceful stars we see, matter is falling into black holes, releasing as much energy as trillions of suns. Neutron stars spin hundreds of times per second, their magnetic fields distorting space around them. Distant quasars shine across billions of light years, powered by black holes consuming the equivalent of stars. And occasionally, a massive star dies, or two neutron stars collide, releasing in seconds more energy than our sun will produce in its entire lifetime. Yet despite these violent extremes, here we are, safely observing from a stable planet orbiting a gentle star in a quiet region of our galaxy. We are far enough from the galactic center and its supermassive black hole to avoid danger. In an era when the universe is calm enough for complex structures like life to exist and persist. The existence of these extreme objects tells us something profound about the universe. The same physical laws that govern the falling of an apple on Earth also govern the behavior of matter near a black hole's event horizon. The same force of gravity that keeps us on the ground also crushes stellar cores into neutron stars and shapes the jets erupting from quasars. The universe operates according to consistent principles, whether we are examining the everyday or the extreme. These cosmic extremes also represent the end stages of stellar evolution, the ultimate fate of matter when gravity and energy reach their greatest intensities. Every black hole was once a star or a collection of stars. Every neutron star began as a massive stellar core. Every gamma-ray burst marks the end of one cosmic story and the beginning of another, scattering heavy elements into space where they may someday form new stars. New planets, perhaps new life. As you rest tonight, consider that the atoms in your body were forged in stars, and some were likely created in the extreme conditions of supernova explosions, perhaps even in events that produce neutron stars or black holes. The gold in any jewelry, the silver in electronics, the platinum in catalytic converters, These elements were almost certainly created in neutron star mergers, forged in the brief, intense moments when two of the densest objects in the universe collided. We are connected to these extremes, built from matter that passed through some of the most violent and energetic processes the universe can produce. Yet from that violence comes creation. The death of one star seeds the birth of others. The merger of neutron stars creates the heavy elements essential for planets and life. Even black holes, seemingly the ultimate destroyers, may play a role in regulating galaxy formation and evolution. The universe is a place of extraordinary contrasts. There is gentleness and violence, creation and destruction, the everyday and the extreme. Black holes and neutron stars exist alongside planets and moons. Quasars and gamma ray bursts punctuate the general calm of cosmic evolution. And in the midst of it all, on a small rocky planet orbiting an ordinary star, conscious beings emerge. Capable of observing these extremes and understanding them, rest peacefully, knowing that you live in a universe rich with wonders, where matter and energy take forms so extreme they strain imagination, yet all operating according to physical laws we can discover and comprehend. The cosmos is vast and sometimes violent, but it is also knowable, and in that knowledge we find both humility and empowerment. How do stars form, live, and die? The story of stars is among the most beautiful narratives in all of science. It is a tale of birth, life, and death, played out over millions or billions of years. A cycle that has repeated countless times since the first stars ignited in the ancient universe. Tonight, as you settle into peaceful rest, let us follow this cosmic journey together. From the cold darkness of stellar nurseries to the spectacular deaths that seed the cosmos with the elements of future generations. Our journey begins in the vast clouds of gas and dust that drift between the stars. The stellar nurseries where new suns are born. These clouds, called nebulae, are among the most beautiful objects in the night sky when viewed through telescopes. They glow with soft colors, reds and blues and greens, illuminated by nearby stars or glowing from their own internal processes. But they are more than merely beautiful. They are cosmic wombs, the places where stars come into existence. A typical stellar nursery is enormous beyond comprehension, often spanning hundreds of light years across and containing enough material to create thousands or even millions of stars. The density is extraordinarily low by earthly standards. In the densest parts of these clouds, there might be a few thousand atoms per cubic centimeter. By comparison, the air you breathe contains about 10 to the 19th power, or 10 billion molecules per cubic centimeter. By our standards, these stellar nurseries are better vacuums than the best laboratory can create. Yet their sheer size means they contain tremendous total mass, hundreds of thousands or millions of times the mass of our Sun. Most of this material is hydrogen, the simplest and most abundant element in the universe, making up about 73% of the cloud's mass. About 25% is helium, and the remaining 2% consists of heavier elements. Everything from carbon and oxygen to iron and gold, all created by previous generations of stars and scattered into space when those stars died. This small fraction of heavy elements is crucial, as we shall see. These nebulae are cold, typically only 10 to 20 degrees above absolute zero. At such low temperatures, atoms move slowly, barely vibrating. The clouds are dark, opaque to visible light, because tiny dust grains, microscopic particles of silicates and carbon, absorb and scatter any light that tries to pass through. If you could float inside such a cloud, you would see nothing but darkness in all directions, perhaps a faint glow from distant stars struggling through the murk. For millions of years, these clouds drift through space, slowly rotating, gradually mixing and churning from the gentle push of magnetic fields and the distant gravitational influences of passing stars. They appear stable, unchanging on human timescales, but they are not eternal. Eventually, something happens to upset their equilibrium. Perhaps a nearby massive star explodes as a supernova, sending a shockwave of compressed gas racing through space. Perhaps two clouds collide in the galaxy's slow rotation. Perhaps the gravitational pull of the galaxy's spiral arms compresses the cloud as it passes through. Whatever the trigger, parts of the cloud begin to collapse under their own gravity. This is the crucial moment, when gravity starts to win its ancient battle against the gas pressure that had been supporting the cloud. Once a region becomes dense enough that its own gravity overcomes the internal pressure, collapse is inevitable. The region contracts, and as it does, it becomes denser, which makes its gravity stronger. which causes it to contract faster. This is a runaway process, what physicists call gravitational instability. But the cloud does not collapse as a single unit. Instead, it fragments into many smaller regions, each collapsing independently. This fragmentation is why stars typically form in clusters rather than in isolation. When we observe young star-forming regions like the Orion Nebula, we see hundreds or thousands of stars being born simultaneously, all from the same parent cloud. As each fragment collapses, it begins to spin faster, conserving angular momentum, just as a figure skater spins faster when pulling in their arms. The spinning causes the collapsing material to flatten into a disk, with most of the mass falling toward the center, while some remains in orbit around it. This disk is important, for it is from such disks that planets eventually form, though that is another story. The center of the collapsing region grows denser and hotter. Gravity converts potential energy into kinetic energy, the energy of motion. The atoms fall inward, gaining speed, and when they collide with other atoms already in the growing core, their kinetic energy converts to heat. The temperature at the center begins to rise. What started as a cold cloud at 10 or 20 degrees above absolute zero gradually warms to hundreds of degrees, then thousands, then millions. This process takes time. For a star like our Sun, the initial collapse from a cloud fragment to a protostar, a hot, dense core not yet generating its own energy through fusion, takes about 100,000 years. This seems long by human standards, but it is remarkably brief in cosmic terms, an eye blink in a story that will unfold over billions of years. The protostar continues to grow, accreting more material from the surrounding disk and envelope. It is not yet a true star, not yet generating energy through nuclear fusion, but it is hot and luminous from the gravitational energy of infalling material. If you could observe it, you would see a glowing object, perhaps 100 times more luminous than our present-day Sun, swaddled in a cocoon of dust and gas, still drawing material from its surroundings. For a Sun-like star, this protostar phase lasts about 10 million years. During this time, the core continues to heat up and compress. The temperature at the center climbs higher and higher, 10,000 degrees, 100,000 degrees, 1 million degrees, 10 million degrees, and then, finally, something remarkable happens. At a core temperature of about 10 million degrees, Kelvin hydrogen nuclei, which are simply protons, begin to fuse together. Normally, protons repel each other because they both carry positive electric charge, and like charges repel. But at 10 million degrees, protons move so fast that when they collide, they can overcome their electrical repulsion and get close enough for the strong nuclear force to take effect, binding them together. Through a series of reactions called the proton-proton chain, 4 hydrogen nuclei fuse to create 1 helium nucleus, 2 positrons, 2 neutrinos, and energy in the form of gamma-ray photons. The helium nucleus has slightly less mass than the 4 protons that created it. The missing mass has been converted directly to energy according to Einstein's famous equation, E equals mc squared. The amount of mass converted is tiny, less than 1% of the original hydrogen mass. But because the speed of light squared is such an enormous number, even this tiny mass loss releases tremendous energy. A single fusion reaction converts about 0.7% of the hydrogen mass to energy. This may not sound like much, but in the Sun's core, about 600 million tons of hydrogen fuse into helium every second, converting about 4 million tons of matter into pure energy every second. When fusion ignites, everything changes. Suddenly, the protostar is generating its own energy, no longer dependent on gravitational contraction. The outward pressure from this nuclear furnace in the core balances the inward pull of gravity. The star stabilizes. The long period of formation is complete. A star has been born. This moment, when a star begins fusing hydrogen in its core, marks the beginning of what astronomers call the main sequence, the long, stable period of a star's life when it steadily converts hydrogen to helium. Our Sun has been on the main sequence for about 4.6 billion years and will remain there for another 5 billion years or so. Most of the stars you see in the night sky are main sequence stars, all engaged in the same fundamental process, fusing hydrogen in their cores. The exact characteristics of a main sequence star depend primarily on its mass. Mass determines everything else: the star's temperature, luminosity, color, size, and most importantly, its lifetime. Low-mass stars, those with less than half the Sun's mass, burn their hydrogen fuel very slowly. They are cool, with surface temperatures of only 3,000 to 4,000 degrees Kelvin, giving them a red color. They are dim, sometimes less than 1,000th as luminous as the Sun, but they are extraordinarily long-lived. A star with 1/10 the Sun's mass will remain on the main sequence for trillions of years, far longer than the current age of the universe. In fact, no low-mass star that has ever formed has yet died of old age. Every red dwarf star that ignited in the early universe is still shining today, slowly working through its hydrogen fuel. Stars like our Sun, with masses between about 1/2 and 1.5 times the solar mass, have intermediate properties. They are yellow or orange, with surface temperatures of 5,000 to 6,000 degrees. They shine steadily for billions of years. The Sun converts about 4 million tons of mass to energy every second. Yet it contains so much hydrogen that this process can continue for about 10 billion years total. High-mass stars, those with more than 8 or 10 times the Sun's mass, live very differently. They are profligate with their fuel, burning through it at an extravagant rate. A star 20 times more massive than the Sun might be 100,000 times more luminous. Its surface temperature might exceed 30,000 degrees Kelvin, giving it a brilliant blue-white color. But such a star will exhaust its hydrogen in only a few million years, perhaps even less than 1 million years for the most massive stars. This inverse relationship between mass and lifetime is one of the beautiful ironies of stellar evolution. The most massive stars, those with the most fuel, are the shortest lived because they burn that fuel so rapidly. The smallest stars with the least fuel live the longest because they burn it so slowly. Life on the main sequence is stable but not unchanging. As a star converts hydrogen to helium in its core, the helium accumulates there like ash in a fireplace. Helium is denser than hydrogen, so the core gradually becomes slightly more compact, slightly denser, which causes the fusion rate to increase slightly, which makes the star gradually become more luminous over time. When our Sun first ignited, 4.6 billion years ago, it was about 70% as luminous as it is today. Over the intervening eons, as helium accumulated in the core, the Sun has gradually brightened. In another billion years or so, the Sun will be bright enough that Earth's oceans will begin to evaporate, making our planet uninhabitable. Long before the Sun leaves the main sequence, life on Earth will face this crisis, though that is far in the future, and intelligent beings may find solutions. But eventually, after millions or billions of years, depending on the star's mass, a crisis arrives. The hydrogen in the core becomes depleted. For stars like the Sun, fusion requires the extreme temperatures and pressures found only in the very center of the star. When the core hydrogen is exhausted, fusion stops there. The nuclear furnace goes out. Without fusion to support it against gravity, the core begins to contract again. This contraction heats the core, just as the original collapse heated the protostar. Meanwhile, a shell of hydrogen surrounding the now inert helium core becomes hot enough to fuse. Hydrogen shell burning begins, with fusion occurring in a thin shell around the core rather than in the center. This changes everything. The energy from shell burning causes the star's outer layers to expand dramatically. The star swells to enormous size, becoming what we call a red giant. The Sun, when it reaches this phase in about 5 billion years, will expand to perhaps 100 times its current diameter, swallowing Mercury and Venus, and possibly reaching Earth's orbit. The surface will cool to about 3,000 degrees as it expands, giving the star a red color, hence the name red giant. At the same time, the core continues to contract and heat up. For a star like the Sun, the core temperature eventually reaches about 100 million degrees Kelvin. At this temperature, something remarkable happens. Helium nuclei begin to fuse together. Helium fusion is more complex than hydrogen fusion. 3 helium nuclei must come together nearly simultaneously to form a carbon nucleus through a process called the triple alpha process. This is less efficient than hydrogen fusion and requires higher temperatures. When helium fusion ignites in the core, it does so suddenly in what is called a helium flash, a brief period when the fusion rate spikes dramatically before stabilizing. The star now has 2 fusion zones, helium burning in the core and hydrogen burning in a shell around it. It stabilizes for a time in this configuration, spending perhaps 100 million years fusing helium into carbon and oxygen in its core. But this phase cannot last indefinitely. Eventually, the helium in the core is exhausted, converted to carbon and oxygen. For stars like the Sun, that is the end of the line. The core is not massive enough to compress further and heat enough to fuse carbon. The final act begins. Fusion now occurs in two shells, a helium-burning shell above the carbon-oxygen core and a hydrogen-burning shell above that. The star becomes unstable. It pulsates, expanding and contracting. Powerful stellar winds begin to blow, carrying away the star's outer layers. Over a few 100,000 years, the star expels much of its mass into space, creating a beautiful, expanding shell of glowing gas called a planetary nebula, though it has nothing to do with planets. The name comes from their appearance through early telescopes, resembling planetary disks. At the center of the expanding nebula, the core remains, a hot, dense ember about the size of Earth, but containing about half the Sun's mass. This is a white dwarf, one of the three possible endpoints for stellar evolution. A white dwarf is no longer generating energy through fusion. It shines simply because it is hot, slowly radiating away its stored thermal energy. But despite being small, it is extraordinarily dense. A teaspoon of white dwarf material would have a mass of about 5 tons. This incredible density is supported not by thermal pressure or fusion energy, but by quantum mechanical effects called electron degeneracy pressure. In ordinary matter, electrons orbit atomic nuclei with plenty of space between them. But in a white dwarf, the matter is compressed so tightly that electrons are squeezed into the smallest possible volume allowed by quantum mechanics. The Heisenberg uncertainty principle prevents them from being compressed further. They resist additional compression with a pressure that does not depend on temperature, making the white dwarf stable even as it cools. A white dwarf starts its existence with a surface temperature of about 100,000 degrees Kelvin, about 20 times hotter than the Sun's surface. It glows brilliant white, hence the name. But with no internal energy source, it can only cool. Over billions of years, it gradually radiates away its heat, fading and cooling, eventually becoming a black dwarf, a cold, dark ember of carbon and oxygen floating through space. However, the universe is not yet old enough for any white dwarf to have cooled completely to a black dwarf. Every white dwarf that has ever formed is still glowing, still slowly cooling. This is the fate awaiting our Sun and most stars in the universe. After 10 billion years on the main sequence, the Sun will become a red giant, then shed its outer layers, leaving behind a white dwarf that will cool slowly over trillions of years, while the expanding nebula of its former outer layers disperses into space, eventually mixing with the interstellar medium and perhaps contributing to future generations of stars. But more massive stars experience very different endings, far more spectacular and violent than the gentle fading of a white dwarf. For stars more massive than about 8 times the Sun, the story continues beyond carbon and oxygen. These stars have massive enough cores to compress further and heat to higher temperatures. When the helium is exhausted, the core contracts again, heats up, and eventually reaches about 600 million degrees, hot enough to fuse carbon. Carbon fusion produces neon and magnesium. When the carbon is exhausted, the core contracts, again, reaching temperatures of about 1 billion degrees, and neon fusion begins. Then oxygen fusion at about 1.5 billion degrees, producing silicon and sulfur. Finally, silicon fusion at about 3 billion degrees, producing iron. Each stage of fusion produces less energy and lasts for a shorter time. A massive star might spend millions of years fusing hydrogen, hundreds of thousands of years fusing helium, a few hundred years fusing carbon, a few years fusing neon, a few months fusing oxygen, and only a few days fusing silicon. The star becomes like an onion, with shells of different elements surrounding the core, each shell fusing its elements while the next inner shell contains the ashes of previous fusion stages. At the end, the core is primarily iron, surrounded by shells of silicon, oxygen, neon, carbon, helium, and hydrogen. Iron is the end of the line. Fusing iron does not release energy, but instead requires energy input. The nuclear furnace has reached a wall it cannot overcome. When the core has converted enough material to iron, disaster strikes suddenly and catastrophically. Without fusion to support it, the iron core collapses. But this is not the gentle contraction experienced earlier. This is a catastrophic implosion occurring in less than 1 second. The core, about the size of Earth, containing more than the Sun's mass, collapses to a sphere only about 20 kilometers in diameter. In 1 second, matter falls inward at speeds of up to 1/4 the speed of light. As the core collapses, protons and electrons are squeezed together so violently that they combine to form neutrons, releasing vast numbers of neutrinos. The collapse continues until the core reaches nuclear density, the density of an atomic nucleus. At this point, the matter cannot be compressed further. It rebounds, like a ball bouncing off a hard surface, sending a shockwave racing outward. This shockwave tears through the star's outer layers, heating them to billions of degrees and triggering explosive nuclear fusion. Elements heavier than iron, which could not be created during the star's normal life, are forged in this brief moment of unimaginable temperatures and pressures. Gold, platinum, uranium, all the heavy elements are created in the explosion. The star explodes as a supernova, suddenly becoming as bright as an entire galaxy of hundreds of billions of stars. For a few weeks, the supernova outshines everything else in its host galaxy. The explosion releases more energy in a few seconds than our Sun will produce in its entire 10 billion year lifetime. Most of this energy, about 99%, is carried away by neutrinos, ghostly particles that barely interact with matter and stream away at the speed of light. The remaining 1%, carried by light and kinetic energy of the exploding material, is still enough to make the supernova visible from hundreds of millions of light years away. The explosion blasts the star's outer layers into space at speeds of 10,000 to 30,000 kilometers per second. This material, enriched with the heavy elements created during the star's life and in the explosion itself, spreads out and eventually mixes with the interstellar medium, becoming part of the nebulae where future stars will form. We are made of this material. Every atom of carbon, oxygen, nitrogen, and heavier elements in your body was created in a star and scattered into space in a supernova explosion. You are quite literally stardust, made of atoms that once existed in stars that died before our Sun was born. But what of the core that collapsed? What remains at the center of the expanding supernova remnant? If the core's mass is between about 1.4 and 3 times the mass of the Sun, it survives as a neutron star, an object we explored in our previous journey. The entire core, more massive than our Sun, has been compressed into a sphere only about 20 kilometers across. It is supported by neutron degeneracy pressure, the same quantum mechanical effect that supports white dwarfs, but at a much higher density. Neutrons are packed together as tightly as possible without forming a black hole. But if the core is even more massive, exceeding about 3 times the Sun's mass, even neutron degeneracy pressure cannot halt the collapse. Nothing in the known universe can prevent complete gravitational collapse. The core continues shrinking, passing the point where light can escape, forming a black hole. An event horizon appears, surrounding a singularity, where all the core's mass is concentrated in a single point of infinite density. The most massive stars, those exceeding perhaps 50 times the Sun's mass, may not even experience a supernova explosion in the traditional sense. Their cores might collapse directly to black holes, with the outer layers simply falling inward, swallowed by the newly formed black hole without being blown away. These events may be less luminous than typical supernovae, or they might produce the hypernovae and long gamma-ray bursts we discussed previously. Thus, stars have 3 possible fates depending on their initial mass. Low and intermediate mass stars, those up to about 8 solar masses, end as white dwarfs, cooling embers supported by electron degeneracy pressure. More massive stars, from about 8 to perhaps 20 or 30 solar masses, explode as supernovae, leaving behind neutron stars. The most massive stars, exceeding 30 solar masses or more, also explode but leave behind black holes, regions from which not even light can escape. All 3 endpoints represent states of matter at the extremes of density and physics. White dwarfs pack half a Sun's worth of mass into an Earth-sized volume. Neutron stars compress more than the Sun's mass into a sphere the size of a city. Black holes concentrate mass into a singularity, a point of infinite density, where our understanding of physics breaks down. The cycle of stellar life and death has been repeating since the first stars ignited in the ancient universe, perhaps 200 million years after the Big Bang. Those first stars were different from stars today. They formed from primordial gas containing only hydrogen, helium, and trace amounts of lithium, with no heavy elements because no stars had yet lived and died to create them. These population 3 stars, as astronomers call them, none of which survive today, were probably very massive, hundreds of times the Sun's mass. They lived brief, brilliant lives, perhaps only a few million years, and died in spectacular supernovae, scattering the first heavy elements into space. These elements mixed with primordial gas, and the next generation of stars, population 2 stars, formed from slightly enriched material. Generation after generation, the cycle repeated. Stars formed from nebulae, lived their lives fusing light elements into heavier ones, and died, returning their enriched material to space. With each generation, the interstellar medium became more metal-rich. Astronomers call any element heavier than helium a metal. Regardless of its chemical properties, our Sun is a population 1 star, formed from gas already enriched by many previous generations. That small fraction of heavy elements in the solar nebula, only about 2%, made all the difference. From those heavy elements came the rocky planets, including Earth. From those elements came the minerals, the atmosphere, the oceans, and eventually, life itself. We exist because stars died. Every breath you take contains oxygen created in the cores of massive stars billions of years ago. The calcium in your bones, the iron in your blood, the carbon in your DNA, all were forged in stellar furnaces and scattered into space in supernova explosions. You are not just in the universe, you are made of the universe, assembled from materials processed through multiple stellar generations. And the cycle continues. Even now, new stars are forming in nebulae throughout the Milky Way and other galaxies. The Orion Nebula, visible to the naked eye as a fuzzy patch in Orion's sword, is a stellar nursery where hundreds of stars are being born. The Eagle Nebula, with its famous pillars of creation, is another active star-forming region. Thousands of such regions exist in our galaxy alone. When our Sun dies in about 5 billion years, it will return most of its mass to the interstellar medium. That material, enriched with carbon and oxygen from the Sun's fusion processes, will eventually mix with other gas and dust. Perhaps 10 billion years from now, it will become part of a new nebula, and from that nebula, new stars will form. Those stars might have planets, and on one of those planets, billions of years in the future, beings might look up at their night sky and wonder about the stars, never knowing that some of the atoms in their bodies once passed through our Sun. This is the grand cycle of stellar evolution, the endless recycling of matter through stars, the gradual enrichment of the universe with heavy elements, the conversion of simple hydrogen and helium into the entire periodic table of elements. It is a story of birth, life, death, and rebirth on cosmic scales, a story that has been unfolding for 13 billion years and will continue for trillions more. As you rest tonight, consider that the light from the stars you see began its journey years, decades, centuries, or millennia ago, depending on the star's distance. That light was produced by fusion in stellar cores, the same process that will eventually lead to those stars' deaths and transformation. Some of the stars you see tonight no longer exist. They have already ended their lives, but their light continues traveling toward us, carrying news of their existence long after they are gone. And consider that you, resting peacefully on this small planet, are intimately connected to all of this. You are part of the cosmic cycle of stellar birth and death. Your body contains atoms that pass through multiple stars, forged in fusion reactions and supernova explosions. In a sense, you are the universe contemplating itself. Star stuff arranged in such a way as to understand stars. The stars shine tonight as they have for billions of years, as they will for billions more. Each one is a nuclear furnace, converting mass to energy, slowly working through its fuel, following the path set by its mass at birth. Low-mass stars will burn slowly for trillions of years. Sun-like stars will shine for billions of years before gently fading as white dwarfs. Massive stars will live fast and die young, exploding as supernovae and leaving behind neutron stars or black holes. The universe is patient. It has time for all these stories to unfold, time for stars to live their full lives, time for their ashes to form new stars, time for complexity to arise from simplicity. And you, living your brief human life, are privileged to understand this cosmic story, to know where you came from and where you are going, to recognize your place in the grand cycle of stellar evolution. Rest peacefully under the light of the stars, those ancient nuclear furnaces, those cosmic recyclers of matter, those engines of complexity in an expanding universe. They have been shining for billions of years before you existed, and they will shine for billions of years after you are gone. But right now, in this moment, you can appreciate them, understand them, and know that you are connected to them in the most fundamental way possible. What is the nature of time and space-time? The nature of time and space, the very fabric of reality itself, is perhaps the most profound mystery we can contemplate. Tonight, as you rest in peaceful stillness, let us explore together these fundamental concepts, journeying through Einstein's revolutionary insights into the structure of the universe and discovering that reality is far stranger and more beautiful than our everyday experience suggests. Before we can understand Einstein's insights, we must first understand what came before. For centuries, humanity believed that space and time were absolute and unchanging. Space was thought to be an empty stage upon which the cosmic drama unfolds, a three-dimensional grid extending infinitely in all directions, the same for everyone everywhere. Time was thought to be a universal river flowing at the same rate for all observers, ticking away uniformly throughout the cosmos. This view seemed obvious from everyday experience. If two events happen simultaneously for one person, surely they happen simultaneously for everyone. If an object has a certain length, surely everyone would measure the same length. If 1 hour passes, surely 1 hour passes for everyone, everywhere. These assumptions were so deeply embedded in human thinking that they seemed self-evidently true, beyond question. Isaac Newton formalized these ideas in the 17th century. His laws of motion and universal gravitation were built on the foundation of absolute space and absolute time. And these laws worked magnificently, describing the motions of planets with exquisite precision, explaining the tides, the trajectories of projectiles, the behavior of pendulums. For more than 200 years, Newtonian physics reigned supreme, apparently explaining all motion in the universe. But in the late 19th century, cracks began to appear in this perfect edifice. Experiments attempting to measure Earth's motion through the supposed luminiferous ether, the medium through which light was thought to propagate, yielded puzzling results. No matter how the experiments were designed, no matter what direction Earth was moving, light always traveled at the same speed. This seemed impossible. If you are running toward a source of light, shouldn't you measure light moving faster toward you? Yet experiments consistently showed that the speed of light was constant, always the same value, approximately 300,000 kilometers per second, regardless of the observer's motion. This puzzle occupied physicists for years. Various explanations were proposed, each more convoluted than the last. And then, in 1905, a young patent clerk in Switzerland named Albert Einstein published a paper that would revolutionize our understanding of reality itself. The paper, titled On the Electrodynamics of Moving Bodies, introduced what we now call the special theory of relativity. Einstein began with two simple postulates. First, the laws of physics are the same in all inertial reference frames, meaning that physics works the same way whether you are at rest or moving at constant velocity. Second, the speed of light in vacuum is constant for all observers, regardless of their motion or the motion of the light source. These two principles seem innocent enough, but their consequences are extraordinary and counterintuitive, overturning our everyday notions of space and time. From these postulates, Einstein derived a startling conclusion. Time and space are not absolute. They are relative, depending on the observer's state of motion. Events that are simultaneous for one observer may not be simultaneous for another observer moving at a different velocity. Time intervals measured by one observer may differ from time intervals measured by another. Lengths measured by one observer may differ from lengths measured by another. Space and time are not separate, independent entities, but are intimately connected, woven together into a four-dimensional fabric called space-time. Let us explore what this means, beginning with the phenomenon called time dilation, perhaps the most famous prediction of special relativity. Imagine you are watching a friend travel past you in a spaceship, moving at a significant fraction of the speed of light. Your friend carries a light clock, a simple device consisting of two mirrors separated by a fixed distance. with a pulse of light bouncing back and forth between them. Each round trip of the light pulse represents one tick of the clock. From your friend's perspective, inside the spaceship, everything seems normal. The light travels straight up to the top mirror, reflects, and travels straight back down. If the mirrors are 1 meter apart, the light travels a total distance of 2 meters per tick. But from your perspective, watching from outside, something different happens. During the time the light pulse travels from the bottom mirror to the top mirror, the entire spaceship has moved forward. The light must therefore travel diagonally, following a longer path to reach the top mirror, which has moved forward during the light's transit. The same happens on the return journey. The light travels a longer diagonal path back to the bottom mirror. Since the speed of light is constant for all observers, one of Einstein's fundamental postulates, and since the light is traveling a longer path from your perspective than from your friend's perspective, it must take more time to complete one tick. Your friend's clock appears to run slowly compared to your own clock. Time is passing more slowly for your friend than for you. This is time dilation, the slowing of time for objects in motion relative to the observer. The faster the relative motion, the more pronounced the effect. At everyday speeds, the effect is negligibly small, far too tiny to notice. But as speeds approach the speed of light, time dilation becomes dramatic. At 90% the speed of light, time passes at about 44% the normal rate. A clock moving at this speed would tick less than half as fast as a stationary clock. At 99% the speed of light, time passes at about 14% the normal rate. At 99.999% the speed of light, time slows to less than 1% of the normal rate. This is not an illusion or a trick of perception. Time genuinely passes at different rates for observers in relative motion. If your friend traveled away from Earth at 99% the speed of light for what seemed to them like 1 year, then returned at the same speed, they would have aged 2 years. But on Earth, more than 14 years would have passed. Your friend would have experienced 2 years while you experienced 14 years. Time itself flowed at different rates for the two of you. This effect has been confirmed countless times through experiments. Atomic clocks flown on airplanes run slightly slower than identical clocks left on the ground, by exactly the amount predicted by relativity. Particles created in the upper atmosphere, called moons, should decay before reaching Earth's surface based on their short lifetimes. But because they travel at nearly the speed of light, time dilation extends their lifetimes from our perspective, allowing them to reach the ground. GPS satellites must account for time dilation in their calculations, or their positioning data would drift out of accuracy by kilometers per day. Time dilation leads to the famous twin paradox, which is not actually a paradox once properly understood. If one twin travels to a distant star at high speed while the other remains on Earth, the traveling twin ages less. When they reunite, the traveler is younger than their Earth-bound sibling. This seems paradoxical because motion is relative. From the traveler's perspective, isn't Earth moving away at high speed? Shouldn't the Earth-bound twin age less? The resolution is that the situation is not symmetric. The traveling twin must accelerate, turn around, and decelerate, changing reference frames, while the Earth-bound twin remains in a single reference frame throughout. The traveling twin genuinely experiences less time, and they are genuinely younger when reunited. This understanding of gravity as curved spacetime makes predictions that differ slightly from Newton's theory. One of the most famous tests occurred during a solar eclipse in 1919. Einstein's theory predicted that light from distant stars would be bent as it passed near the Sun, following the curved spacetime around the Sun. The amount of bending differed from what Newton's theory predicted. During the eclipse, when stars near the Sun became visible, astronomers measured the positions of stars appearing close to the Sun's edge and found they had shifted by exactly the amount Einstein predicted. Light had been deflected by the Sun's gravitational field, or more accurately, light had followed a curved path through the space-time curved by the Sun's mass. This bending of light by gravity is now called gravitational lensing, and it has become an important tool in astronomy. When light from a distant galaxy passes near a massive object like a galaxy cluster, the cluster's gravity bends the light, often creating multiple distorted images of the background galaxy. By studying these distortions, astronomers can map the distribution of mass in the foreground cluster, including dark matter that cannot be observed directly. Gravitational lensing reveals the invisible mass shaping space-time. The curvature of space-time is not just a property of exotic objects like black holes. Every mass curves spacetime around it. Earth curves spacetime, which is why objects fall and why the moon orbits us. You curve spacetime around yourself by a minuscule amount. The book sitting on your table curves spacetime. Everything that has mass or energy curves spacetime, though usually the effect is too small to notice. The amount of curvature depends on the mass and energy density. The Sun, containing about 330,000 times Earth's mass, curves spacetime significantly in its vicinity. The supermassive black hole at the center of our galaxy, containing 4 million solar masses, curves spacetime dramatically. Near such massive compact objects, spacetime becomes strongly curved, and strange effects emerge. One consequence of curved spacetime is that the shortest distance between 2 points is not necessarily a straight line in ordinary space. Near a massive object, the shortest path through spacetime follows a curve in space. Light takes the quickest path through spacetime, which may appear curved in space. Time and space mix together in curved spacetime in ways that defy our intuitions based on flat space. Another consequence is frame dragging, the dragging of spacetime itself by rotating massive objects. A rotating mass does not just curve spacetime, but twists it, pulling nearby spacetime around in the direction of rotation. This effect, also called the Lenz-Thirring effect, has been measured near Earth using satellites with incredibly precise gyroscopes. The gyroscopes slowly rotate due to spacetime being dragged by Earth's rotation, exactly as general relativity predicts. Near rotating black holes, frame dragging becomes extreme. The black hole drags spacetime around with it so strongly that nothing within a certain distance, called the ergosphere, can remain stationary. Everything within the ergosphere must rotate in the direction the black hole rotates, dragged along by rotating spacetime itself. Perhaps the most dramatic prediction of general relativity is the existence of gravitational waves, ripples in spacetime itself propagating outward at the speed of light. When massive objects accelerate, particularly in asymmetric ways, they create disturbances in spacetime that spread outward like ripples on a pond. These waves carry energy away from the system producing them. For many decades, gravitational waves remained theoretical, predicted by equations but never directly observed. Then, on September 14, 2015, two enormous detectors called LIGO detected a gravitational wave passing through Earth. The signal lasted only a fraction of a second, but it was unmistakable. The detectors measured spacetime itself oscillating, stretching and compressing by an amount far smaller than the width of an atomic nucleus as the wave passed by. The wave had been produced by two black holes, each about 30 times the mass of the Sun, spiraling together and merging 1.3 billion light-years away. In the final moments before merger, the black holes were orbiting each other hundreds of times per second, moving at significant fractions of the speed of light, creating powerful distortions in spacetime. When they finally merged, the collision released more power in the form of gravitational waves than all the stars in the observable universe combined were emitting as light at that moment. 3 solar masses of energy, converted entirely to gravitational waves through Einstein's E equals mc squared, spread outward as ripples in spacetime itself. Since that first detection, many more gravitational wave events have been observed from black hole mergers, neutron star mergers, and mixed mergers. Each detection is a direct observation of spacetime curvature changing dynamically, confirming Einstein's century-old prediction and opening a new window on the universe. Gravitational wave astronomy allows us to observe events invisible to traditional telescopes, to study black holes directly, and to test general relativity in its strongest regimes. The curvature of spacetime has profound implications for cosmology, the study of the universe as a whole. General relativity predicts that the universe itself can expand or contract, with the distance between galaxies increasing or decreasing over time. This is not galaxies moving through space, but rather space itself expanding, carrying galaxies along with it. In an expanding universe, the fabric of spacetime itself stretches. A light wave traveling through expanding space gets stretched along with it, increasing its wavelength and shifting it toward the red end of the spectrum. This cosmological redshift is what we observe when we look at distant galaxies. The farther a galaxy is, the more space has expanded during the light's journey, and the more the light is redshifted. This is distinct from the Doppler shift caused by motion through space. Cosmological redshift is caused by the expansion of space itself. The expansion of the universe can be described mathematically using solutions to Einstein's field equations. These equations relate the curvature of space-time to the distribution of matter and energy. Solving them for a homogeneous, isotropic universe gives various possible cosmological models, depending on the density and properties of matter and energy. Current observations indicate our universe is approximately flat on large scales, meaning that if you could travel in a straight line through space-time indefinitely, you would never curve back to your starting point. Space-time extends forever in all directions, or at least as far as we can determine. A flat universe is a special case, balanced between positive curvature, which would eventually curve back on itself like the surface of a sphere, and negative curvature, which would continue expanding forever and spread out in a saddle shape. The expansion of the universe is currently accelerating, driven by dark energy, which acts like a negative pressure in space itself, pushing space to expand faster. This acceleration means the large-scale curvature of space-time is changing over time, with distant regions receding from us ever more rapidly. Black holes represent the most extreme curvature of space-time possible. At the center of a black hole lies a singularity, a point where curvature becomes infinite and our mathematical description of space-time breaks down. The singularity is surrounded by an event horizon, the boundary beyond which space-time is curved so strongly that all paths lead inward, and nothing can escape, not even light. Space-time near a black hole behaves in bizarre ways. Time and space partially exchange roles. Outside the event horizon, you can move freely in space, but are compelled to move forward in time. Inside the event horizon, you can move freely in the time direction, but are compelled to move inward in space, toward the singularity. Reaching the singularity becomes as inevitable as reaching the next moment in time. This strange mixing of space and time is a consequence of extreme space-time curvature. The study of quantum effects in curved space-time has led to another remarkable prediction. Stephen Hawking showed that black holes are not entirely black. Quantum fluctuations near the event horizon can result in the creation of particle-antiparticle pairs, with one particle falling into the black hole while the other escapes. From a distance, this appears as radiation being emitted by the black hole. Black holes slowly evaporate through this Hawking radiation, losing mass over immense timescales. This process connects general relativity, which describes space-time curvature, with quantum mechanics, which describes the behavior of particles and fields. Understanding this connection fully requires a theory of quantum gravity, which physicists have been seeking for decades. General relativity describes gravity beautifully on large scales, and quantum mechanics describes the other forces perfectly on small scales. But the two theories are fundamentally incompatible. Reconciling them into a single framework remains one of the greatest challenges in theoretical physics. The nature of time itself remains mysterious in many ways. Why does time flow in one direction, from past to future? Why do we remember the past but not the future? These questions touch on thermodynamics and the arrow of time, the observation that entropy, disorder, increases over time. Yet the fundamental laws of physics are time-symmetric. They work equally well running forward or backward in time. The arrow of time we experience may be connected to the initial conditions of the universe, to the low entropy state of the Big Bang, but this remains an active area of research. Another mystery is whether time had a beginning and whether it will have an end. In the Big Bang model, time itself began with the universe. Asking what happened before the Big Bang may be meaningless, like asking what is north of the North Pole. If time began, then there was no before, no earlier moment from which the universe emerged. Time and space came into existence together. Similarly, depending on the universe's fate, time may or may not have an end. In a heat-death scenario, time continues forever, but the universe approaches maximum entropy, and meaningful change ceases. In a Big Crunch or Big Rip scenario, space-time itself might end. The nature of time at these extremes pushes the boundaries of our understanding. As you rest tonight, consider that you are not just occupying a point in space at a moment in time. You are an extended object in four-dimensional space-time, a world line connecting your birth to your death, and your conscious experience is a moving slice through this four-dimensional structure, a sequence of moments that you experience as the flow of time. Consider that time passes at different rates depending on motion and gravity, that simultaneity is relative, that space contracts for objects in motion. What seems like solid, absolute reality is actually fluid and observer-dependent. Space and time are not the stage on which the cosmic drama unfolds. They are part of the drama itself, dynamic and changeable, curved by mass and energy. The massive objects in the universe, stars and planets, galaxies and black holes, do not move through space-time pulled by gravitational forces. They curve space-time around them, and they follow the natural contours of that curved geometry. Earth orbits the Sun not because any force pulls it, but because that is the straightest path through the space-time curved by the Sun's mass. Light from distant stars bends around galaxies not because gravity pulls on photons, but because light follows the curves in space-time created by those galaxies. Gravitational waves ripple through space-time itself when massive objects accelerate, stretching and compressing space and time as they pass, carrying information about cataclysmic events billions of light years away. You are embedded in this curved space-time, experiencing its geometry. The passage of time you feel, the solidity of space you perceive, these are your experience of the local geometry of space-time in Earth's weak gravitational field. If you could travel near a black hole, you would experience space-time's geometry very differently, with time slowing dramatically and space becoming strangely distorted. Every massive object curves space-time around it. The Sun creates a valley in space-time, and Earth rolls around the rim of that valley. Earth creates its own smaller valley, and the Moon orbits in that curved geometry. You create a tiny, nearly imperceptible curve in space-time, simply by existing, simply by having mass. You are not just in space-time, you shape it, however slightly. The universe is not a collection of objects existing in empty space and evolving through time. It is a four-dimensional space-time continuum, curved and shaped by the matter and energy it contains, dynamic and ever-changing. Space expands, carrying galaxies apart. Black holes curve space-time so strongly that they trap light. Gravitational waves propagate as ripples in the very fabric of reality. And through it all, time remains perhaps the deepest mystery. Why does it flow in one direction? What is the present moment? And why does it seem to move? Is time fundamental, or is it emergent from some deeper level of reality? These questions touch the foundations of physics and philosophy, probing the nature of existence itself. As Einstein himself wrote, the distinction between past, present, and future is only a stubbornly persistent illusion. In the space-time view of reality, all moments exist equally. The past has not ceased to exist, and the future is not yet to come. They are simply different locations in space-time, just as here and there are different locations in space. Your entire life, from birth to death, exists as a complete structure in space-time, a four-dimensional world line through the cosmos. Yet you experience time flowing, moment following moment, consciousness moving through space-time like a spotlight illuminating successive frames of a film. Why we have this experience, why the flow of time seems so real and immediate, remains mysterious. Rest peacefully in the knowledge that you exist in a universe far stranger and more beautiful than everyday experience suggests. Space and time are not what they seem. They are relative, unified, curved by mass and energy. You move through four-dimensional space-time on a trajectory shaped by Earth's gravity, following a geodesic through curved geometry. Time flows at different rates in different locations. Simultaneity is not absolute, and the fabric of reality itself can stretch, compress, and ripple. These are not mere abstractions or mathematical curiosities. They are the fundamental nature of the reality you inhabit. GPS satellites account for relativistic effects, or they would fail. Particle accelerators rely on time dilation to extend the lifetimes of fast-moving particles. Gravitational lensing reveals distant galaxies and invisible dark matter. Gravitational wave detectors measure ripples in space-time from cosmic collisions billions of light years away. The universe operates according to these principles, and we are part of it. Four-dimensional beings extended through space-time, experiencing sequential slices as the flow of time, embedded in geometry curved by the mass of Earth and Sun and galaxy, connected to all of space-time through its unified structure. What are the fundamental forces and particles that govern the universe? The universe, in all its complexity and grandeur, operates according to remarkably few fundamental principles. Tonight, as you drift into peaceful contemplation, let us explore together the deepest level of physical reality we currently understand, the fundamental forces and particles that govern everything, from the smallest subatomic interactions to the largest cosmic structures, the building blocks and rules from which all of existence emerges. At the most fundamental level we can currently probe, the universe is composed of a small number of elementary particles interacting through four fundamental forces. Everything you see, touch, and experience, every atom, every molecule, every structure in the cosmos, is built from these basic ingredients following these simple rules. Understanding this foundation is to glimpse the underlying code of reality itself. Let us begin with the four fundamental forces, the ways that matter and energy interact, the mechanisms through which the universe operates. The first and most familiar is gravity, the force we experience every moment of our lives. Gravity keeps your feet on the ground, holds the moon in orbit around Earth, binds our planet to the sun, and shapes the structure of galaxies and the universe itself. Of the four fundamental forces, gravity is by far the weakest. Yet because it acts over infinite range and is always attractive, never repulsive, it dominates on large scales where enormous masses accumulate. As we explored in our previous journey through space-time, gravity, according to Einstein's general relativity, is not truly a force in the conventional sense, but rather the curvature of space-time by mass and energy. Yet for most purposes, we can think of gravity as a force, an attraction between all objects that have mass or energy. The strength of gravitational attraction depends on the masses involved and the distance between them, growing stronger with greater mass and weaker with greater distance, specifically decreasing with the square of the distance. Despite being the weakest force, gravity shapes the universe on cosmic scales because it has infinite range and because massive objects accumulate. A galaxy containing hundreds of billions of stars has enormous total mass, and gravity binds all those stars together. Gravity causes gas clouds to collapse and form stars. It drives the collision and merger of galaxies. It shapes the cosmic web structure we observe on the largest scales. Gravity is the architect of cosmic structure, yet gravity plays almost no role at the atomic scale. The gravitational attraction between two protons in an atomic nucleus is 40 orders of magnitude. That is 1 followed by 40 zeros, weaker than the electromagnetic force between them. At subatomic scales, gravity is utterly negligible, completely overwhelmed by the other forces. The second fundamental force is electromagnetism, which unifies two phenomena that appear distinct in everyday life: electricity and magnetism. In the 19th century, James Clerk Maxwell showed that these are two aspects of the same underlying force, two manifestations of the electromagnetic field. Electromagnetism is responsible for almost everything in your daily experience except gravity. The solidity of matter, the chemical bonds holding molecules together, the transmission of nerve signals in your brain, the light by which you see, the heat you feel, the colors you perceive, all arise from electromagnetic interactions. When you touch a table, you do not actually contact its atoms. The electrons in your hand and the electrons in the table repel each other electromagnetically, creating a barrier that feels like solid contact. Electromagnetism acts between particles that carry electric charge. Like charges repel each other and opposite charges attract, the force is much stronger than gravity, about 40 orders of magnitude stronger at typical atomic distances. A charged particle creates an electromagnetic field around itself, and this field exerts forces on other charged particles. The range of electromagnetic force is infinite, like gravity. But unlike gravity, electromagnetic forces can be attractive or repulsive. Most matter in the universe is electrically neutral overall, containing equal numbers of positive and negative charges that cancel out. This is why electromagnetic forces do not dominate on cosmic scales the way gravity does. Stars and planets contain vast numbers of protons and electrons, but they have equal amounts of positive and negative charge, leaving them essentially neutral. Gravity, which is always attractive and never cancels, wins on large scales. But at atomic scales, electromagnetism reigns supreme. The structure of atoms, the behavior of electrons orbiting nuclei, the formation of chemical bonds, all these arise from electromagnetic interactions. Chemistry is essentially applied electromagnetism. The properties of materials, whether something is a metal or insulator, hard or soft, transparent or opaque, all depend on how electromagnetic forces arrange electrons in atoms and molecules. Light itself is an electromagnetic phenomenon, waves in the electromagnetic field propagating through space. When an electron in an atom jumps from one energy level to another, it emits or absorbs a photon, a quantum of electromagnetic energy. All the light in the universe from the glow of distant stars to the warmth of sunlight on your face, consists of photons, the force-carrying particles of electromagnetism. The third fundamental force is the strong nuclear force, also called the strong interaction or color force. This force binds quarks together to form protons and neutrons, and it binds protons and neutrons together to form atomic nuclei. Without the strong force, matter as we know it could not exist. The strong force is aptly named. It is approximately 100 times stronger than electromagnetism at the distances where it operates, making it by far the strongest of the four fundamental forces. But unlike gravity and electromagnetism, which extend to infinite distances, the strong force has very short range, operating only over distances of about 1 femtometer, or 10 to the power of negative 15 meters, roughly the size of an atomic nucleus. This short range is why we do not experience the strong force directly in everyday life. It operates only within the nucleus, binding nuclear particles together, but its consequences are profound. The strong force overcomes the electromagnetic repulsion between protons, which all carry positive charge and would otherwise repel each other, preventing atomic nuclei from forming. Without the strong force, only hydrogen, with its single proton nucleus, could exist. There would be no heavy elements, no complex chemistry, no molecules, no life. The strong force also stores enormous amounts of energy in atomic nuclei. Nuclear fission, the splitting of heavy nuclei, and nuclear fusion, the combining of light nuclei, both release energy because they allow nucleons to rearrange into more tightly bound configurations. The sun shines by fusing hydrogen into helium, releasing the binding energy of the strong force. Nuclear weapons and nuclear power derive their immense energy from the same source. Interestingly, the force we call the strong nuclear force binding protons and neutrons in nuclei is actually a residual effect of a more fundamental force binding quarks inside protons and neutrons. Just as molecules are held together by residual electromagnetic forces between atoms that are themselves electrically neutral overall, nuclei are held together by residual strong forces between protons and neutrons that are themselves color neutral, a concept we will explore further. The fourth and final fundamental force is the weak nuclear force, responsible for certain types of radioactive decay and for processes essential to the sun's energy production. The weak force is stronger than gravity but weaker than electromagnetism and the strong force. And like the strong force, it operates only over extremely short ranges, even shorter than the strong force, at distances of about 0.1 femtometers. The weak force can change one type of quark into another type, which allows protons to transform into neutrons and vice versa. This process is called beta decay. When a free neutron decays into a proton, electron, and antineutrino, that transformation occurs through the weak force. The weak force is also responsible for neutrino interactions. Neutrinos interact with other matter almost exclusively through the weak force, which is why they pass through ordinary matter so easily. Trillions of neutrinos from the sun pass through your body every second, and virtually none of them interact with your atoms. Despite being called weak, this force is essential for life. In the sun's core, the first step of hydrogen fusion requires 2 protons to fuse into a deuterium nucleus, which consists of 1 proton and 1 neutron. This requires one of the protons to transform into a neutron through the weak force. This step is the bottleneck in solar fusion, proceeding very slowly because the weak force is relatively weak and short-ranged. This slowness is fortunate. If the weak force were stronger, the sun would burn through its hydrogen fuel far more quickly, and stars would have much shorter lifetimes, giving life less time to evolve. These 4 forces, gravity, electromagnetism, the strong force, and the weak force, govern all interactions in the universe. Every phenomenon, from the falling of raindrops to the explosion of supernovae, from the firing of neurons to the collision of galaxies, can be traced to one or more of these fundamental forces acting on fundamental particles. Speaking of fundamental particles, let us now explore what the universe is made of at its deepest level. The current framework describing elementary particles and their interactions through 3 of the 4 forces, all except gravity, is called the Standard Model of Particle Physics, developed gradually over the 20th century and confirmed through countless experiments. The Standard Model is one of the most successful and precisely tested theories in all of science. According to the Standard Model, Matter is composed of two types of fundamental particles called fermions, quarks and leptons. These particles are truly fundamental, meaning they have no internal structure and are not made of anything smaller, at least as far as we can currently determine. Quarks are the building blocks of protons and neutrons, and therefore of atomic nuclei. There are 6 types of quarks, which physicists call flavors. In order of increasing mass, they are named up, down, charm, strange, top, and bottom. These whimsical names should not obscure their fundamental importance. Quarks combine in groups of 3 to form baryons, including protons and neutrons, or in quark-antiquark pairs to form mesons. A proton consists of 2 up quarks and 1 down quark, bound tightly together by the strong force. A neutron consists of 1 up quark and 2 down quarks. The up and down quarks are the lightest and most stable quarks, which is why they make up ordinary matter. The other 4 quark types, charm, strange, top, and bottom, are heavier and unstable, quickly decaying into lighter quarks. These heavier quarks existed in the early universe when temperatures were extreme, and they can be created briefly in high-energy particle collisions, but they do not exist in ordinary matter today. Quarks have a property called color charge, which has nothing to do with visual color, but is analogous to electric charge. Just as electric charge comes in positive and negative, color charge comes in 3 types conventionally called red, green, and blue, along with their anticolors. The strong force acts between particles with color charge, binding quarks together. A crucial property of the strong force is color confinement. Quarks can never be isolated individually. They are always bound together in combinations that are color neutral. 3 quarks of different colors, red, green, and blue, combine to form color-neutral protons and neutrons. A quark and its antimatter antiquark combine to form color-neutral mesons. If you try to pull 2 quarks apart, the energy you invest creates new quark-antiquark pairs, which immediately bind with the quarks you were trying to separate. You never end up with an isolated quark, but only with new combinations of quarks. This is why we never observe free quarks, and it is why the strong force has such unusual properties. At very short distances within a proton, quarks move relatively freely, a phenomenon called asymptotic freedom. But try to separate them, and the force grows stronger with distance, unlike any other force we know. The strong force is mediated by particles called gluons, which we will discuss shortly. The second type of matter particle in the standard model is leptons. There are 6 types of leptons, also coming in pairs. The most familiar lepton is the electron, the negatively charged particle orbiting atomic nuclei. The electron has 2 heavier cousins, the muon and the tau, which are essentially heavier, versions of the electron with identical properties except mass. Muons and taus are unstable, quickly decaying into electrons and other particles. Each of these charged leptons has an associated neutrino, the electron neutrino, muon neutrino, and tau neutrino. Neutrinos are electrically neutral, extraordinarily light, and interact only through the weak force and gravity. They pass through ordinary matter, almost as if it were not there. A neutrino could pass through a light year of solid lead and have only a 50% chance of interacting with even a single atom. Neutrinos are produced copiously in nuclear reactions, including those in the sun's core and in supernova explosions. Every second, about 65 billion neutrinos from the sun pass through every square centimeter of your body. Yet you never feel them because they almost never interact with your atoms. Detecting neutrinos requires massive detectors and long observation times to catch the rare occasions when a neutrino does interact. For many years, neutrinos were thought to be massless, but experiments have shown they have tiny masses, far smaller than even the electron, which is the lightest charged particle. Neutrinos can also oscillate, changing from one type to another as they travel. An electron neutrino produced in the sun might arrive at Earth as a muon neutrino or tau neutrino. This oscillation reveals subtle properties of neutrino physics still being actively researched. So quarks and leptons are the matter particles, the building blocks of everything in the universe. But how do these particles interact? How are forces transmitted between them? This is where force carrier particles enter the picture. In quantum field theory, which underlies the Standard Model, forces are mediated by particles called bosons. When two charged particles repel or attract electromagnetically, they do so by exchanging photons, the particles of light. When quarks are bound by the strong force, they exchange gluons. The weak force is mediated by W and Z bosons. Even gravity, though not included in the Standard Model, is thought to be mediated by hypothetical particles called gravitons, though gravitons have never been detected and may be impossible to detect directly. The photon is the force carrier of electromagnetism. Photons are massless particles that travel at the speed of light, the cosmic speed limit. They carry electromagnetic force between charged particles. When you see light, your eyes are detecting photons. When charged particles interact electromagnetically, they are exchanging virtual photons, quantum fluctuations in the electromagnetic field that exist briefly to mediate the interaction. Photons can have different energies, corresponding to different wavelengths or frequencies of light. Low-energy photons are radio waves. Higher energy photons are microwaves, then infrared, then visible light, then ultraviolet, then X-rays, then gamma rays. All are photons, differing only in energy. The entire electromagnetic spectrum, from the longest radio waves to the shortest gamma rays, consists of photons of different energies. The strong force is mediated by 8 types of gluons. Gluons carry color charge themselves, unlike photons which do not carry electric charge. This property makes the strong force behave very differently from electromagnetism. Because gluons carry color charge, they interact not only with quarks but also with other gluons. This self-interaction gives the strong force its unique properties, including confinement and asymptotic freedom. The weak force is mediated by 3 bosons, the W+, W-, and Z bosons. Unlike photons and gluons, these particles are very massive, about 80 to 90 times the mass of a proton. This large mass is the reason the weak force has such short range. Massive force carriers cannot travel far before being reabsorbed, limiting the force's range according to quantum mechanics. The W and Z bosons were predicted by theory and discovered. In 1983 at CERN, the European Particle Physics Laboratory, confirming a crucial prediction of the Standard Model. Their discovery helped solidify our understanding of how the weak force operates and how it relates to electromagnetism. This brings us to one of the most profound insights of 20th century physics. The weak force and electromagnetism, though they appear very different, are actually 2 aspects of a single unified force called the electroweak force. At high energies, such as those present in the early universe shortly after the Big Bang, the electromagnetic and weak forces are indistinguishable, unified into the electroweak interaction. Only when the universe cooled did this symmetry break, causing the forces to manifest differently, with the weak force having massive carriers and short range, while electromagnetism has massless carriers and infinite range. This unification is governed by a mechanism involving something called the Higgs field, a field that permeates all of space. Particles interact with the Higgs field, and this interaction gives them mass. Particles that interact strongly with the Higgs field, like W and Z bosons, acquire large masses. Particles that do not interact with the Higgs field, like photons, remain massless. Most of the mass of ordinary matter, however, does not come from the Higgs field, but from the binding energy of quarks in protons and neutrons, a consequence of the strong force. The quantum of the Higgs field is a particle called the Higgs boson, predicted in 1964 by several physicists, including Peter Higgs. The Higgs boson was the last unobserved particle predicted by the Standard Model. Finding it became one of the highest priorities in particle physics. Finally, in 2012, experiments at CERN's Large Hadron Collider detected the Higgs boson with a mass of about 125 times the proton mass. This discovery completed the Standard Model and confirmed our understanding of how particles acquire mass. The Standard Model also includes antimatter, predicted by Paul Dirac in 1928 and confirmed experimentally shortly thereafter. For every particle, there exists an antiparticle with the same mass but opposite charge and other quantum numbers. The antiparticle of the electron is the positron, identical to an electron but positively charged. Quarks have antiquarks. When a particle meets its antiparticle, they annihilate, converting their mass entirely into energy according to E equals mc squared. Antimatter is not exotic or rare in particle physics. It is created constantly in high-energy processes, in particle accelerators, in cosmic ray collisions in the atmosphere, and in certain types of radioactive decay. However, antimatter is rare in the universe at large. The observable universe consists almost entirely of matter, not antimatter. Why this asymmetry exists, why the universe contains more matter than antimatter, is one of the great unsolved mysteries of physics. Shortly after the Big Bang, matter and antimatter should have been created in equal amounts, and they should have annihilated each other, leaving a universe of pure energy. Yet somehow, a slight excess of matter over antimatter existed, about one extra matter particle for every billion matter-antimatter pairs. All the matter we see today, every star, planet, and galaxy, comes from that tiny imbalance. The Standard Model successfully describes almost all phenomena we can observe at particle colliders. Its predictions have been tested to extraordinary precision. For instance, the magnetic moment of the electron, a quantity measuring how the electron responds to magnetic fields, has been calculated and measured to agree within 1 part in a trillion, making it one of the most precisely confirmed predictions in all of science. Yet despite its tremendous success, the Standard Model is incomplete. It does not include gravity. It provides no explanation for dark matter, which makes up 27% of the universe's content. It does not explain why neutrinos have mass, a fact discovered after the Standard Model was developed, though extensions to the model can accommodate neutrino masses. It does not explain the matter-antimatter asymmetry. It contains about 20 parameters, numbers that must be measured experimentally, but are not predicted by the theory, such as particle masses and force strengths. Why do these parameters have the values they do? The Standard Model does not say. Most fundamentally, the Standard Model treats gravity separately from the other 3 forces. The holy grail of theoretical physics is a unified theory, often called a theory of everything, that would incorporate all 4 fundamental forces into a single consistent framework, ideally describing all particles and forces as different manifestations of a single unified structure. Some unification has already been achieved. The electroweak theory unified electromagnetism and the weak force. Physicists believe that at even higher energies, the strong force also unifies with the electroweak force in what is called a grand unified theory, or GUT. Such unification would have existed in the extremely early universe, when temperatures were almost unimaginably high. Within the first tiny fraction of a second after the Big Bang, several candidate theories attempt to unify all forces, including gravity. String theory proposes that fundamental particles are not point-like, but are actually tiny vibrating strings of energy. Different vibration modes of these strings correspond to different particles. String theory naturally includes gravity and potentially unifies all forces, but it requires extra spatial dimensions beyond the 3 we observe, and it has proven extremely difficult to test experimentally. Another approach is loop quantum gravity, which attempts to quantize space-time itself, describing space and time as composed of discrete elements rather than being continuous. This approach focuses on reconciling general relativity with quantum mechanics directly, rather than embedding both in a larger structure like string theory does. Other theoretical frameworks include supersymmetry, which proposes that every known particle has a heavier supersymmetric partner, and various approaches to quantum gravity. None of these theories has been confirmed experimentally, and many physicists debate which approach is most promising. The search for a theory of everything is driven partly by aesthetic considerations, the desire for a simple, elegant description of nature, but also by practical necessity. Our current theories break down under extreme conditions. At the singularity of a black hole, or at the moment of the Big Bang, both general relativity and quantum mechanics apply, yet they give inconsistent results. Understanding these regimes requires a theory that unifies them. The unification program in physics has a long and successful history. Newton unified terrestrial and celestial mechanics, showing that the same laws govern falling apples and orbiting moons. Maxwell unified electricity and magnetism. Einstein unified space and time. The electroweak theory unified electromagnetism and the weak force. Each unification revealed that phenomena that appeared distinct are actually aspects of a deeper unity. Physicists believe this pattern will continue, eventually revealing that all forces and particles are manifestations of a single fundamental structure. Meanwhile, experiments continue pushing the boundaries of our knowledge. The Large Hadron Collider probes higher energies than ever before, searching for new particles beyond the standard model. Experiments hunt for dark matter particles, which must exist, but are not part of the standard model. Neutrino experiments study the subtle properties of these ghostly particles. Gravitational wave detectors open new windows on the universe. Each experiment tests our theories and searches for phenomena that might point beyond current understanding. As you rest tonight, consider that you are made of fundamental particles governed by fundamental forces. Every atom in your body consists of electrons bound to nuclei by electromagnetism. Each nucleus contains protons and neutrons bound by the strong force. Inside each proton and neutron, quarks dance bound by gluons. Occasionally, a neutron in your body decays through the weak force, though this is rare and harmless. Gravity holds you to Earth, and Earth to the Sun. The forces acting within your body at this moment are the same forces operating in the heart of the Sun, in colliding galaxies, in the first moments after the Big Bang. The particles making up your atoms are identical to particles that existed in the early universe and to particles created in supernova explosions. There is a deep unity to the physical world, a small number of elementary ingredients combining according to simple rules to create all the complexity we observe. The universe operates according to these fundamental principles at every scale. Quarks combine to form protons and neutrons. Protons and neutrons combine to form nuclei. Nuclei and electrons combine to form atoms. Atoms combine to form molecules. Molecules combine to form cells. Cells combine to form organisms. And yet, at the foundation of all this complexity are a few dozen types of fundamental particles interacting through 4 fundamental forces. This reductionist view does not diminish the wonder of existence, but enhances it. Complex structures and behaviors emerge from simple rules. The richness of chemistry arises from electromagnetic interactions between electrons. The diversity of life emerges from complex arrangements of molecules, themselves built from atoms, themselves built from elementary particles. Reality is layered, with each level having its own patterns and principles, yet all ultimately grounded in the fundamental forces and particles. The fact that we can understand these fundamentals, that through observation and reasoning we can uncover the deepest layers of reality, is itself remarkable. The universe is comprehensible. Its behavior follows patterns we can discover and describe mathematically. The same laws operate everywhere and at all times, or at least everywhere and at all times we can observe. This universality allows us to understand distant galaxies and ancient epochs, to predict particle collisions and cosmic evolution. Yet mysteries remain. Why does the universe operate according to these particular laws and not others? Why do the fundamental constants have the values they do? Is there a deeper level beneath what we currently consider fundamental? Are strings or quantum geometry or something even stranger the true foundation? Can we achieve complete unification, a theory of everything that explains all phenomena within a single elegant framework? These questions drive research at the frontiers of physics. Every experiment tests our theories and searches for new phenomena. Every observation of the cosmos probes the fundamental laws under extreme conditions. Every theoretical advance attempts to reveal deeper unifying principles. The search continues, generation after generation, gradually revealing more about the fundamental nature of reality. Rest peacefully in the knowledge that the universe, for all its vastness and complexity, operates according to principles we can understand. 4 fundamental forces and a few dozen types of elementary particles, interacting according to mathematical laws, give rise to everything from atoms to galaxies, from stars to consciousness. You are part of this magnificent structure, built from the universe's fundamental ingredients, governed by its fundamental laws, connected to everything from quarks to quasars through the same underlying physics. The forces acting right now within every atom of your body have been operating since the beginning of time, binding particles together, enabling structure and complexity, making possible molecules and chemistry, and ultimately life. The particles making up your atoms are truly fundamental, the deepest level of reality we currently understand, the ultimate constituents of everything that exists. How do we search for life beyond Earth and understand our own solar system? The question of whether we are alone in the universe is among the most profound inquiries humanity has ever undertaken. Tonight, as you settle into peaceful rest, let us explore together the search for life beyond Earth, the remarkable worlds within our own solar system that might harbor living organisms, and the thousands of distant planets where life might have taken hold under alien suns. Life as we know it requires certain fundamental ingredients. While we can imagine exotic forms of life based on different chemistry or operating under different principles, we must begin our search with what we understand, looking for life similar to life on Earth because that is the only example we have. And all life on Earth, from the simplest bacterium to the largest whale, from deep-sea thermal vent organisms to high-altitude birds, shares certain basic requirements. The first and most crucial ingredient is liquid water. Water is essential to all known life. It serves as a solvent, a medium in which the chemistry of life can occur. Complex organic molecules dissolve in water, allowing them to interact, combine, and form the intricate structures necessary for living organisms. Water's unique properties, its ability to dissolve both polar and non-polar substances, its expansion when freezing, which prevents bodies of water from freezing solid from the bottom up, its high heat capacity, which moderates temperature changes, all make it extraordinarily well suited to support life. Life on Earth exists virtually everywhere liquid water can be found. Microorganisms thrive in Antarctic ice, in boiling hot springs, in the depths of the ocean, in acidic lakes, in radioactive waste, and kilometers beneath Earth's surface. If water is present and temperatures allow it to remain liquid, life finds a way to survive there. This observation drives the mantra of astrobiology. Follow the water. When searching for life beyond Earth, we look first for places where liquid water exists or existed in the past. The second ingredient is organic molecules, complex molecules based on carbon. Carbon is uniquely suited to form the backbone of biological molecules because of its ability to form 4 strong chemical bonds, allowing it to create an almost infinite variety of complex structures, including long chains, branch structures, and rings. Organic molecules include amino acids, which link together to form proteins, nucleotides, which form DNA and RNA, lipids, which form cell membranes, and sugars, which store energy and form structural materials. Remarkably, organic molecules are not rare in the universe. They form naturally in interstellar space, in the atmospheres of planets and moons, and in comets. Meteorites that fall to Earth often contain amino acids and other organic compounds. The raw materials of life appear to be common throughout the cosmos, suggesting that if the conditions are right, the chemistry that leads to life might begin in many places. The third essential ingredient is energy. Life requires a continuous source of energy to maintain its complex organization, to grow, to reproduce, to respond to its environment. On Earth's surface, most life ultimately derives its energy from sunlight through photosynthesis. But this is not the only option. Deep beneath the ocean, far from any sunlight, ecosystems thrive around hydrothermal vents, powered by chemical energy released when minerals dissolved in hot water react with seawater. These chemosynthetic organisms demonstrate that sunlight is not necessary for life. Chemical energy can suffice. So the search for life beyond Earth focuses on finding environments where liquid water, organic molecules, and energy sources coexist. Remarkably, several worlds in our own solar system appear to meet these criteria, places where life might exist right now, waiting to be discovered. Let us begin our tour of potentially habitable worlds with Mars, Earth's neighboring planet, a cold desert world that appears barren and lifeless today, but may not always have been so. Mars today is a harsh environment. Its atmosphere is thin, about 1% the density of Earth's atmosphere, composed mostly of carbon dioxide. Surface temperatures average about -60 degrees Celsius, cold enough to freeze carbon dioxide into dry ice. Liquid water cannot exist on the surface under these conditions. Any water that melts immediately evaporates in the thin atmosphere or refreezes. But Mars was not always this way. Abundant evidence reveals that ancient Mars, more than 3 billion years ago, had a thicker atmosphere, warmer temperatures, and liquid water flowing across its surface. Orbital images show ancient river valleys carved by flowing water, deltas where rivers emptied into lakes or seas, and minerals that form only in the presence of water. Mars once had lakes, perhaps even an ocean covering much of its northern hemisphere. For perhaps the first billion years of its history, Mars may have been quite Earth-like, with a water cycle, rainfall, and conditions potentially suitable for life. What happened? Mars is smaller than Earth, with only about 1/10 Earth's mass. Its lower gravity could not hold onto its atmosphere as effectively as Earth. Additionally, Mars lacks a global magnetic field, which Earth possesses due to its liquid iron core. Earth's magnetic field shields our atmosphere from the solar wind, the stream of charged particles flowing from the sun. Without such protection, Mars's atmosphere was gradually stripped away by the solar wind over hundreds of millions of years. As the atmosphere thinned, surface water evaporated or froze, and Mars transformed into the cold desert we see today. But the possibility remains that life arose on ancient Mars when conditions were more favorable, and that microbial life might persist even today in protected subsurface environments. Mars almost certainly has liquid water underground. The planet's interior retains heat from its formation and from radioactive decay. Deep beneath the surface, temperatures are warm enough for water to remain liquid. In 2018, radar observations detected what appears to be a lake of liquid water about 1.5 kilometers beneath Mars's south polar ice cap. If life exists on Mars today, it likely survives in such subsurface environments, protected from the harsh surface conditions, accessing liquid water and deriving energy from chemical reactions with minerals. Earth has extensive subsurface ecosystems, microorganisms living in rock fractures and pore spaces kilometers below the surface, sustained by chemical energy rather than sunlight. Similar life might exist on Mars. Multiple missions have explored Mars, searching for evidence of past or present life. The Viking landers in the 1970s conducted experiments designed to detect metabolism by microorganisms in Martian soil, with ambiguous results still debated today. More recent rovers, Spirit, Opportunity, Curiosity, and Perseverance, have explored ancient lakebeds and river deltas, finding evidence that these environments once had all the ingredients necessary for life: liquid water, organic molecules, and chemical energy sources. Perseverance, which landed in 2021, is currently collecting rock samples from an ancient river delta in Jezero Crater, a site that once held a deep lake. These samples will eventually be returned to Earth by future missions, where they can be analyzed in detail for any signs of ancient Martian life. Finding even fossil microorganisms on Mars would be one of the most profound discoveries in human history, proving that life arose independently on two different planets in the same solar system, suggesting that life is common throughout the universe. But Mars is not the only promising location. Even more intriguing are several moons of the outer planets that appear to have vast oceans of liquid water beneath their icy surfaces. Europa, a moon of Jupiter slightly smaller than Earth's moon, is covered by a shell of water ice estimated to be 15 to 25 kilometers thick. But beneath this ice lies an ocean containing more water than all of Earth's oceans combined. This ocean is kept liquid by tidal heating. Europa orbits Jupiter in an elliptical orbit, and Jupiter's immense gravity flexes Europa's interior as it orbits closer and farther away. This constant flexing generates heat through friction, enough to keep the subsurface ocean liquid despite the moon's great distance from the sun. Europa's surface shows clear evidence of this subsurface ocean. The ice shell is crisscrossed with cracks and ridges, patterns suggesting the ice floats on liquid water and breaks and refreezes as the moon flexes. Some regions appear to be relatively young geologically, where warm ice has welled up from below and resurfaced. Most excitingly, observations suggest that plumes of water vapor occasionally erupt from the surface, geysers shooting water from the subsurface ocean into space. If Europa's ocean exists, and all evidence suggests it does, then it provides all the ingredients for life. Liquid water in abundance, check. Organic molecules, likely present from the same processes that delivered them throughout the solar system, check. Energy sources, potentially from hydrothermal vents on Europa's ocean floor, where the rocky core meets the ocean, similar to Earth's deep sea vents, check. The ocean floor would be in complete darkness, but as Earth's vent ecosystems demonstrate, sunlight is not necessary. Chemical energy can sustain life. Could life exist in Europa's ocean? Nothing we know about biology makes it impossible. The ocean has existed for billions of years, plenty of time for life to arise and evolve. The environment might be similar to Earth's deep oceans, cold and dark but habitable. Complex ecosystems might swim in those dark waters, sustained by chemical energy from the ocean floor. NASA is planning the Europa Clipper mission, scheduled to launch in 2024, to study Europa in detail, characterizing its ice shell and ocean, and searching for plumes where the ocean's water reaches the surface. If plumes are active, a future mission might fly through them, collecting samples of ocean water and analyzing them for organic molecules or even microorganisms. We might detect life on Europa without ever landing, simply by sampling its plumes. Another Jovian moon, Ganymede, also appears to have a subsurface ocean, though deeper and less accessible than Europa's. And at Saturn, we find two more promising worlds. Enceladus, a small moon only about 500 kilometers in diameter, has proven to be one of the most exciting targets in the search for life. In 2005, the Cassini spacecraft discovered enormous plumes of water vapor and ice crystals erupting from cracks near Enceladus's south pole, geysers shooting material hundreds of kilometers into space. These plumes are fed by a subsurface ocean that exists beneath the ice in at least the moon's southern hemisphere, possibly globally. Cassini flew through these plumes multiple times, directly sampling material from Enceladus's ocean. The plumes contain water vapor, ice crystals, salt, and organic molecules, including complex carbon compounds. Most significantly, the plumes contain molecular hydrogen, which on Earth is produced by reactions between hot water and rock at hydrothermal vents. The presence of hydrogen suggests that Enceladus has active hydrothermal vents on its ocean floor, providing chemical energy that could support life. Enceladus appears to have all the necessary ingredients for life, and it is actively offering samples of its ocean water for us to study. A future mission could sample these plumes more thoroughly, searching for biosignatures, chemical or molecular evidence of life. If life exists in Enceladus's ocean, we might be able to detect it without even landing on the moon. Saturn's largest moon, Titan, is unique in the solar system, the only moon with a substantial atmosphere, actually thicker than Earth's atmosphere. Titan's atmosphere is mostly nitrogen, like Earth's, but it contains methane, which creates an organic chemistry unlike anywhere else we can observe. Titan is cold, far colder than anywhere life exists on Earth, with surface temperatures around -180 degrees Celsius. At such temperatures, water ice is as hard as rock and cannot serve as a solvent for life's chemistry. But Titan has lakes and seas of liquid methane and ethane on its surface, entire hydrological cycles where methane evaporates, forms clouds, falls as rain, and flows in rivers back to the lakes. Could life exist in liquid methane at extremely cold temperatures? This would require biochemistry fundamentally different from Earth's water-based life, but some scientists have speculated it might be possible. Titan also has evidence of a subsurface water ocean beneath its icy crust, similar to Europa and Enceladus, where more conventional water-based life might exist. Titan thus offers two potential habitats: a cryogenic surface environment with exotic chemistry, and a subsurface water ocean. NASA and ESA are planning the Dragonfly mission, a drone-like rotorcraft that will fly through Titan's atmosphere, landing at multiple sites to study the moon's organic chemistry and search for signs of past or present life. Dragonfly is scheduled to arrive at Titan in the late 2030s. Even beyond these prime targets, other worlds show promise. Pluto, despite being far from the Sun and incredibly cold, appears to have a subsurface ocean. Several other moons of Jupiter and Saturn might have subsurface oceans. The variety of potentially habitable environments in our solar system has expanded dramatically in recent decades, transforming the search for life from a distant dream into an achievable scientific goal. If life is found on Mars or Europa or Enceladus, the next crucial question is whether it arose independently or shares a common origin with Earth life. Early in solar system history, when planets and moons were being heavily bombarded by asteroids and comets, material was exchanged between worlds. A large impact on Mars can blast rocks into space, and some of those rocks eventually fall to Earth as Martian meteorites. We have found such meteorites, rocks that formed on Mars and traveled to Earth. Similarly, Earth rocks have been blasted to Mars. If life arose on Earth and was then transported to Mars on a meteorite, then Martian life would be related to Earth life, sharing the same origin. Alternatively, life might have arisen on Mars first and been transported to Earth. Or life might have arisen independently on both worlds. Distinguishing these possibilities would require detailed analysis of any life we discover, examining its biochemistry and genetic material if it has any, comparing it to Earth life. Finding life elsewhere in the solar system, even microbial life, would profoundly impact our understanding of life's prevalence in the universe. If life arose independently multiple times in one solar system, then the universe must be teeming with life. Every star might have planets, and every suitable planet might develop life given enough time. The cosmos could be full of living worlds. This brings us to exoplanets, planets orbiting stars other than our Sun. Until 1995, we knew of no planets beyond our solar system. We assumed other stars had planets, but we had no proof. Then, in 1995, astronomers detected the first confirmed exoplanet orbiting a Sun-like star, opening a new era in astronomy. Since then, we have discovered more than 5,000 confirmed exoplanets, with thousands more candidates awaiting confirmation. We now know that planets are extremely common. Most stars have planets. Our galaxy likely contains hundreds of billions of planets, possibly more planets than stars. Many of these planets are in their star's habitable zone, the range of distances where temperatures allow liquid water to exist on a planet's surface. Exoplanets are detected primarily through two methods. The transit method observes the slight dimming of a star's light when a planet passes in front of it from our perspective, blocking a tiny fraction of the star's light. The radial velocity method detects the subtle wobble in a star's motion caused by the gravitational pull of an orbiting planet. Both methods have been tremendously successful, revealing a diversity of planetary systems far exceeding what we imagined. We have found planets of every size, from smaller than Earth to larger than Jupiter. We have found planets orbiting closer to their stars than Mercury orbits our Sun, with surface temperatures exceeding 1,000 degrees. We have found planets in the habitable zones of their stars, at distances where temperatures might allow liquid water. We have found planets orbiting binary star systems, where two suns rise and set. We have found planets around small red dwarf stars and around sun-like yellow stars. The search now focuses on finding Earth-like planets in habitable zones and characterizing their atmospheres. When a planet transits in front of its star, some of the star's light passes through the planet's atmosphere. Different gases absorb light at specific wavelengths, leaving fingerprints in the star's spectrum. By analyzing this light, we can determine what gases are present in the exoplanet's atmosphere. This is how we search for biosignatures, atmospheric gases that might indicate the presence of life. On Earth, oxygen makes up about 21% of our atmosphere, but this oxygen is almost entirely produced by photosynthetic organisms. Without life constantly replenishing it, oxygen would react with rocks and other materials and disappear from the atmosphere within a few million years. An atmosphere containing significant oxygen, especially combined with gases like methane which react with oxygen, suggests ongoing biological production. Other potential biosignatures include phosphine, a gas produced by certain microorganisms on Earth and recently controversially claimed to have been detected in Venus's atmosphere, though this detection remains disputed. Certain combinations of gases, such as oxygen and methane together, might be especially strong indicators of life because these gases react with each other and should not coexist in large quantities without ongoing production. Several exoplanets have been characterized in some detail. TRAPPIST 1, a small red dwarf star about 40 light-years away, has 7 Earth-sized planets, at least 3 in the star's habitable zone. These planets have been studied with the James Webb Space Telescope, which is capable of detecting gases in their atmospheres. Early results have been disappointing, with some planets appearing to have little or no atmosphere, perhaps stripped away by radiation from the star's youth. But observations continue, and other planets in the system remain promising targets. Proxima Centauri b, a planet orbiting the closest star to our Sun, just over 4 light-years away, orbits in its star's habitable zone. Proxima Centauri is a red dwarf, smaller and cooler than our Sun, so the habitable zone is much closer to the star. The planet might have liquid water, but it might also be tidally locked with one side always facing the star, creating extreme temperature differences. Whether such a planet could support life remains uncertain. Dozens of other exoplanets are being studied as potential habitats for life. The James Webb Space Telescope, launched in 2021, is revolutionizing exoplanet science with its ability to detect fainter signals and characterize atmospheres in unprecedented detail. Other proposed missions, like the Habitable Exoplanet Observatory being studied by NASA, would be specifically designed to image and characterize Earth-like planets around nearby stars. The search for life beyond Earth also includes SETI, the search for extraterrestrial intelligence, which looks not for microbial life, but for technologically advanced civilizations that might be broadcasting radio signals or other signs of their presence. Since 1960, radio telescopes have been scanning the sky for artificial signals, narrowband radio transmissions that would not occur naturally and would indicate intelligent design. So far, SETI searchers have found nothing conclusive. The famous WOW signal detected in 1977 remains unexplained, but has never repeated, and might have been terrestrial interference. The absence of detected signals does not mean intelligent life does not exist. Space is vast, and we have searched only a tiny fraction of possible frequencies and directions. A civilization must be broadcasting at the right frequency in our direction at the time we are listening. The probability of such coincidence is small. The Fermi paradox captures the puzzle. If life is common, and if some fraction of life develops intelligence and technology, then where is everybody? Our galaxy is billions of years old enough for civilizations to have arisen, developed interstellar travel, and colonized the entire galaxy many times over. Yet we see no evidence of such civilizations. No megastructures, no signs of large-scale engineering, no visitors. The sky is silent. Many explanations have been proposed. Perhaps life is rare. Perhaps intelligence is rare. Perhaps technological civilizations inevitably destroy themselves before achieving interstellar travel. Perhaps they exist but have no interest in colonizing the galaxy or in broadcasting signals we could detect. Perhaps they exist but are so different from us that we do not recognize their presence. Perhaps interstellar travel is simply too difficult, too expensive, too slow to be practical even for advanced civilizations. Perhaps we are the first, the earliest technological civilization in our galaxy, and others will follow. We do not know which, if any, of these explanations is correct. But the search continues, and our tools improve constantly. Every new exoplanet discovered, every atmosphere characterized, every potentially habitable world identified brings us closer to answering the ancient question, are we alone? As you rest tonight, consider that you live in a remarkable time. For all of human history until very recently, we could only wonder about other worlds. Now we know they exist, thousands of them, with more discovered constantly. We know that the ingredients for life are common throughout the universe. We know that potentially habitable environments exist on multiple worlds in our own solar system, and likely on countless exoplanets. Within your lifetime, we may discover life beyond Earth, microbial life on Mars or Europa or Enceladus, biosignatures in an exoplanet's atmosphere, perhaps even a signal from an intelligent civilization. Any of these discoveries would fundamentally transform our understanding of our place in the cosmos. Or we might find nothing, might discover that life, despite suitable conditions existing in many places, is extraordinarily rare, perhaps unique to Earth. This too would be profound, suggesting that we are alone, that Earth is precious beyond measure, that consciousness and intelligence may exist nowhere else in the observable universe. Either answer, we are not alone, or we are alone, carries tremendous implications. The universe appears to be full of places where life could exist. Liquid water, organic molecules, and energy sources are common throughout the cosmos. The question is whether these ingredients actually give rise to life, whether the transition from non-living chemistry to living organisms is easy or difficult, common or rare. We do not yet know how life began on Earth. Was it a likely outcome of chemistry in a suitable environment, something that happens naturally wherever conditions permit? Or was it an extraordinarily unlikely accident, a confluence of improbable events that might never be repeated? Finding even simple microbial life elsewhere would answer this question. If life arose independently multiple times, then the transition from chemistry to biology cannot be impossibly difficult. The universe should be full of living worlds. Even if most harbor only microorganisms and complex life is rarer, the search continues on many fronts. Rovers explore Mars, drilling into rocks and analyzing samples. Missions are planned to Europa and Enceladus to sample their oceans. Telescopes characterize exoplanet atmospheres, searching for biosignatures. Radio telescopes listen for signals. Every avenue is pursued, every possible sign of life investigated. We are searching for our cosmic family, for other instances of the phenomenon we represent, for other arrangements of matter that have become alive, that grow and reproduce and evolve, that perhaps eventually develop intelligence and technology and wonder, as we do, whether they are alone. The ingredients are there, scattered throughout the cosmos. Water in vast quantities on moons and planets, organic molecules forming naturally in interstellar space and planetary atmospheres, energy from sunlight and from chemical reactions. The same basic materials that led to life on Earth exist in countless other locations. Whether they have taken that next step, whether chemistry has become biology elsewhere, remains one of the greatest open questions in science. Sleep peacefully, knowing that humanity is actively searching for life beyond Earth, using the most sophisticated tools ever developed. That within the coming decades we may find microbes on Mars or Europa, that we may detect biosignatures in the atmosphere of a distant exoplanet, that we may discover we are not alone in the universe, or alternatively, that we are unique alone, extraordinarily precious. The search itself is ennobling, reaching beyond our world to understand our place in the cosmos, asking whether the universe that gave rise to life here has done so elsewhere, whether the path that led from simple molecules to human consciousness has been followed on other worlds around other stars. These questions are being answered now, in your lifetime, through patient observation and careful analysis, through robotic explorers on Mars and spacecraft at Jupiter and Saturn, through telescopes studying distant worlds. The universe is vast, filled with hundreds of billions of galaxies, each containing hundreds of billions of stars, most with planets. The numbers are staggering, and yet we have found life on only one world, the planet beneath you, the Earth that is your home. Whether life is common or rare, abundant or unique, we will discover through continued searching, through exploring our solar system and studying distant exoplanets, through listening to the cosmos and investigating every promising lead. What are the most puzzling, unsolved mysteries in modern cosmology? The universe, for all that we have learned about it, remains deeply mysterious. Tonight, as you drift into peaceful contemplation, let us explore together the greatest unsolved puzzles of modern cosmology, the questions that keep scientists awake at night, the mysteries that challenge our understanding of reality itself and hint at profound truths still waiting to be discovered. We begin with perhaps the most humbling mystery in all of science, the realization that we do not know what most of the universe is made of. As we have explored in previous journeys, observations tell us that ordinary matter, the atoms that make up everything we can see and touch, accounts for only about 5% of the universe's total mass and energy content. The remaining 95% consists of dark matter and dark energy, substances whose fundamental nature remains completely unknown despite decades of intensive research. Dark matter, comprising about 27% of the universe, reveals itself only through its gravitational effects. We know it exists because galaxies rotate too quickly for the amount of visible matter they contain. By all calculations, these galaxies should tear themselves apart, with stars on their outer edges flying away into intergalactic space. Yet they hold together, rotating at speeds that can only be explained if they are embedded in massive halos of invisible matter, typically extending 10 times farther than the visible galaxy and containing 10 times more mass. We observe dark matter's effects on many scales. Galaxy clusters contain more mass than we can account for with visible matter. Gravitational lensing, the bending of light around massive objects, reveals that clusters contain far more mass than their visible galaxies and hot gas. Computer simulations of cosmic structure formation match observations only when we include dark matter in the calculations. The cosmic microwave background radiation shows patterns consistent with dark matter influencing the early universe. Yet after decades of searching, we have never directly detected a single dark matter particle. We do not know what it is made of. The most popular hypothesis suggests dark matter consists of WIMPs, weakly interacting massive particles, a new type of elementary particle not included in the standard model. These particles would interact with ordinary matter only through gravity and possibly the weak nuclear force, making them extraordinarily difficult to detect. Experiments around the world search for dark matter particles, deep underground, shielded. From cosmic rays that might create false signals, sensitive detectors wait for a dark matter particle to collide with an atomic nucleus. These experiments use various materials, from liquid xenon to germanium crystals to argon, each chosen for its sensitivity to particular types of dark matter particles. The detectors can sense individual atomic nuclei recoiling from collisions, but distinguishing genuine dark matter interactions from background noise requires extraordinary precision. So far, these experiments have found nothing conclusive. Every few years, an experiment reports a possible signal, a slight excess of events that might indicate dark matter interactions. But these hints never strengthen into definitive detections. Either dark matter interacts even more weakly with ordinary matter than expected, making it effectively invisible to current detectors, or it is something other than WIMPs entirely. Alternative candidates include axions, extremely light particles, predicted by theories addressing other physics puzzles. Axions would behave very differently from WIMPs, forming a sort of invisible fog permeating the galaxy, rather than discrete particles zipping through space. Other proposals suggest dark matter might be primordial black holes, formed in the very early universe rather than from stellar collapse. Or perhaps dark matter consists of particles we have not yet imagined, requiring entirely new physics beyond our current theories. The mystery deepens when we consider that dark matter shaped the universe's structure. In the early universe, dark matter's gravity pulled ordinary matter into denser regions, seeding the formation of galaxies and the cosmic web. Without dark matter, the universe would look completely different. Galaxies might not have formed at all, or would have formed much later and in different patterns. In a very real sense, we exist because dark matter exists, yet we do not know what it is. Some scientists have proposed that dark matter does not exist at all, that instead, our understanding of gravity is wrong. Perhaps gravity behaves differently on galactic scales than Einstein's general relativity predicts. Various modified gravity theories have been proposed, attempting to explain galactic rotation without invoking dark matter. But these theories struggle to explain all the observations. They might account for galaxy rotation, but fail to explain galaxy cluster dynamics, or gravitational lensing, or the cosmic microwave background patterns. Dark matter, despite being invisible and undetected, remains the best explanation we have for multiple independent observations. But if dark matter is mysterious, dark energy is profoundly enigmatic, perhaps the deepest mystery in all of physics. Dark energy comprises about 68% of the universe, the majority of everything that exists. It was discovered in 1998 when two teams of astronomers studying distant supernova made an astonishing finding. They expected to measure the universe's expansion slowing down over time due to gravity. Instead, they found the expansion is accelerating. Distant galaxies are not just moving away from us, they are moving away faster and faster as time passes. Something is pushing the universe apart, counteracting gravity's attractive pull and causing space itself to expand at an accelerating rate. This something has been named dark energy, but the name tells us nothing about what it actually is. We observe its effects clearly, measuring the acceleration with increasing precision, but we have no idea what causes it. The simplest explanation is that dark energy is the cosmological constant, a property of space itself, according to quantum field theory. Even empty space is not truly empty, but seethes with quantum fluctuations, virtual particles constantly popping into and out of existence. These fluctuations give empty space an inherent energy density, which would act exactly like dark energy, pushing space to expand. This sounds promising until we try to calculate the magnitude of this vacuum energy. Quantum field theory predicts a value for the cosmological constant that is larger than what we observe by a factor of 10 to the power of 120, A1 followed by 120 zeros. This is not just wrong, it is spectacularly wrong. Perhaps the worst prediction in the history of physics. Observed dark energy is tiny compared to what theory naively predicts. Why is the cosmological constant so small? Why does it have the particular value we observe rather than some other value? These questions have no answer. Perhaps dark energy is not a cosmological constant, but something dynamical, a field that changes over time, sometimes called quintessence. Such a field might explain why dark energy has its particular value today, though it requires introducing new physics, and raises its own questions about why this field exists and what determines its properties. Or perhaps our understanding of gravity is incomplete on cosmic scales. Just as modified gravity theories have been proposed to explain galactic dynamics without dark matter, other modifications have been suggested to explain cosmic acceleration without dark energy. But these face similar challenges, struggling to match all observations consistently. The consequences of dark energy are profound and somewhat unsettling. If dark energy continues to dominate and the universe continues to accelerate, then in the distant future, distant galaxies will recede beyond our observable horizon. Trillions of years from now, observers in our galaxy will see far fewer galaxies than we see today. Eventually, all galaxies outside our local group will disappear from view, having been carried by cosmic expansion to distances so great that their light can never reach us. The universe will appear much emptier, darker, lonelier than it appears now. Ultimately, if dark energy remains constant, the universe faces heat death, a cold, dark, empty future where stars have burned out, black holes have evaporated, and nothing remains but isolated particles in an ever-expanding void. If dark energy grows stronger over time, the universe might end in a big rip, where accelerating expansion eventually tears apart galaxies, stars, planets, atoms, and perhaps even space-time itself. That we understand so little about dark energy, which dominates the universe and determines its ultimate fate, is both humbling and exciting. There is so much yet to discover, so much fundamental physics we do not understand. Dark energy might be our first glimpse of physics beyond Einstein's relativity and the Standard Model, a clue pointing toward deeper truths about the nature of space, time, and energy. Let us turn now to another profound mystery, one that goes back to the very beginning of the universe: the matter-antimatter asymmetry. For every type of particle, there exists an antiparticle with the same mass but opposite charge and other quantum numbers. The electron has the positron. Quarks have antiquarks. When a particle meets its antiparticle, they annihilate, converting their entire mass into energy. This symmetry between matter and antimatter is fundamental to particle physics, and the Big Bang should have created equal amounts of both. In the extremely hot, dense conditions of the early universe, energy was constantly converting into particle-antiparticle pairs, and these pairs were constantly annihilating back into energy. As the universe expanded and cooled, eventually the temperature dropped below the point where new particles could be created. All the existing particles and antiparticles should have found each other and annihilated, leaving a universe filled with nothing but photons, the particles of light that carry away the energy from matter-antimatter annihilation. But that is not what happened. Somehow, there was a slight excess of matter over antimatter, approximately one extra matter particle for every billion matter-antimatter pairs. After nearly all matter and antimatter annihilated each other, this tiny excess remained. Every atom in the observable universe today, every star, planet, and galaxy, every atom in your body comes from that small imbalance. We exist because the universe contained slightly more matter than antimatter in the first moments after the Big Bang. Why was there this asymmetry? The laws of physics as we currently understand them are nearly symmetric between matter and antimatter. There are small violations of this symmetry in the weak nuclear force, discovered in the 1960s and studied extensively since then. These violations show that certain processes proceed slightly differently for matter than for antimatter. But the observed violations are far too small to account for the matter-antimatter asymmetry we observe in the universe. Several theoretical mechanisms have been proposed. Perhaps in the very early universe, when temperatures were extraordinarily high, particles existed that do not exist today, massive particles that decayed preferentially into matter rather than antimatter, creating the observed excess. Perhaps the asymmetry arose during cosmic inflation, quantum fluctuations creating slightly more matter than antimatter as inflation ended. Perhaps symmetry violation in processes we have not yet observed is much larger than in the processes we have studied. Or perhaps the answer is even more radical. Some theories suggest that antimatter is not missing, but exists in separate regions of space, entire galaxies or galaxy clusters made of antimatter rather than matter. We would not easily distinguish antimatter stars and galaxies from matter ones, as both emit identical light. The boundary regions between matter and antimatter domains would produce distinctive signatures from matter-antimatter annihilation, but perhaps such boundaries are rare or distant enough that we have not observed them. Most cosmologists consider this unlikely, as it requires explaining how matter and antimatter separated into distinct regions. But the possibility remains. The matter-antimatter asymmetry is not just an academic puzzle. It is personal. You exist only because of this asymmetry. Had the universe contained exactly equal amounts of matter and antimatter, annihilation would have been complete. No atoms would remain, only photons filling an empty universe. No stars, no planets, no life. The fact that we exist to ask the question proves the asymmetry occurred. But understanding why remains one of the deepest mysteries in cosmology. This brings us to perhaps the most mind-bending mystery of all, the possibility of a multiverse and the question of what, if anything, existed before the Big Bang. The Big Bang theory describes the universe's evolution from an extremely hot, dense state nearly 14 billion years ago. But what came before that? What caused the Big Bang? Did time itself begin with the Big Bang, making the question of before meaningless? Or did something exist earlier, some previous state or structure from which our universe emerged? One intriguing possibility is cosmic inflation, which we have discussed before. Inflation proposes that the universe underwent a period of exponentially rapid expansion in its first fraction of a second, driven by a special field called the inflaton. When inflation ended, the energy stored in the inflaton field converted into particles and radiation, essentially creating all the matter and energy in the universe in a process sometimes called reheating. This reheating is, in some sense, the hot Big Bang, the moment when the universe as we normally think of it began. But what drove inflation? And what existed before inflation began? Some versions of inflationary theory suggest that inflation, once started, is eternal. Quantum fluctuations ensure that while inflation ends in some regions, creating bubble universes like ours, it continues in other regions. New bubble universes constantly form, each undergoing its own inflation and reheating, creating its own space and time. In this eternal inflation scenario, our observable universe is just one bubble in an infinite foam of universes, each potentially with different properties, different laws of physics, different values of physical constants. This is one version of the multiverse hypothesis. The word multiverse encompasses several distinct ideas, not all compatible with each other. The eternal inflation multiverse is one type. Another arises from string theory, which suggests that the fundamental constants and forces we observe depend on how extra spatial dimensions are curled up. There might be an enormous number of ways, perhaps 10 to the power of 500 or more, to configure these extra dimensions, each giving rise to a universe with different physics. All these possible universes might exist somewhere in a vast string theory landscape. Another type of multiverse comes from quantum mechanics. The many worlds interpretation suggests that every quantum measurement causes the universe to split into multiple branches, each representing a different possible outcome. In one branch, you are reading this sentence. In another, you pause to think about something else. In another, you fell asleep. Every quantum event creates new branches, leading to an ever-expanding tree of parallel universes. Yet another multiverse concept comes from mathematical physics, the idea that every mathematically consistent structure exists as a universe somewhere. Our universe is described by certain mathematical equations, certain laws of physics, certain initial conditions, but other mathematical structures, other possible laws might describe other universes. If mathematical existence and physical existence are the same, then every possible universe exists somewhere in a mathematical multiverse. These multiverse ideas are controversial, and many physicists are skeptical. The main criticism is that multiverse theories are not testable. If other universes exist beyond our observable universe, beyond any possible causal contact with us, then we can never observe them, never gather evidence about them, never test predictions about them. Are they science or speculation? Can a theory be scientific if it makes predictions about things that are inherently unobservable? Proponents argue that multiverse theories make testable predictions about our universe. Eternal inflation makes predictions about the patterns we should see in the cosmic microwave background. String theory, while it allows many possible universes, might eventually predict which one we inhabit based on consistency requirements. Even the many worlds interpretation makes predictions about quantum probabilities that differ slightly from other interpretations. Moreover, some argue that we already have indirect evidence for a multiverse. Why do the fundamental constants of nature have the particular values they do? Why is the cosmological constant so small? Why is the ratio of electron mass to proton mass what it is? These values appear fine-tuned for life. Change them slightly, and stars would not form, or atoms would be unstable, or chemistry would be impossible, and life could not exist. One explanation is the anthropic principle. If a vast multiverse exists with different physical constants in different regions, then only those regions with constants compatible with life will be observed by living beings. We observe values compatible with life not because they are special or preferred, but because we could not exist in regions with different values. This is a selection effect. The universe appears fine-tuned because we exist in a universe capable of producing observers. In the vast multiverse, most regions are lifeless, but we necessarily find ourselves in a rare region where life is possible. This anthropic reasoning makes some physicists deeply uncomfortable. It seems to abandon the search for deeper explanations, accepting instead that some properties of our universe are accidental, selected from a vast ensemble by the requirement that we exist to observe them. Yet if the multiverse is real, anthropic reasoning might be necessary to explain some observations. The question of what existed before the Big Bang touches on the nature of time itself. In classical general relativity, time begins at the Big Bang singularity. Asking what happened before is like asking what is north of the North Pole. The question is meaningless because time itself did not exist before. But quantum mechanics might change this picture. As we approach the Big Bang singularity, both gravity and quantum mechanics become important. We need a theory of quantum gravity to describe what happens, but we do not yet have such a theory. Various approaches, string theory, loop quantum gravity, and others, suggest different possibilities. Some quantum gravity theories suggest the Big Bang singularity is not a true beginning, but rather a transition. Perhaps the universe existed before in a different state, contracted to a minimum size, and then bounced into the expansion we observe, in what is called a Big Bounce scenario. Perhaps time is cyclic, with each big crunch followed by a new Big Bang, an eternal cycle of expansion and contraction, each cycle giving birth to a new universe with possibly different properties. Perhaps our universe is a quantum fluctuation, arising from nothing or from some quantum vacuum state, or from a higher dimensional space. Stephen Hawking proposed that in quantum cosmology, the universe might have no boundary in time, that asking what came before the Big Bang is meaningless, not because time began abruptly, but because near the beginning, time becomes like another dimension of space in ways that make the concept of before inapplicable. These ideas push the boundaries of science into territory where observation becomes difficult or impossible and where mathematics and philosophy merge. Yet they address genuine questions. Why does the universe exist? Why does it have the properties it has? Are the laws of physics arbitrary or necessary? Is our universe unique or one among many? We may never answer these questions definitively. The earliest moments of the universe, the potential multiverse, the nature of time itself, these may lie forever beyond direct observation. Yet we continue to probe the boundaries of the knowable, using observations of our universe to constrain theories, searching for testable predictions, refining our understanding incrementally. Some mysteries may have surprising solutions. Dark matter might be discovered tomorrow in a deep underground detector, finally revealing its nature after decades of searching. A theoretical breakthrough might explain dark energy, showing it to be a natural consequence of quantum gravity. Patterns in the cosmic microwave background, or in the distribution of galaxies, might provide evidence for or against eternal inflation and the multiverse. Other mysteries might persist indefinitely. We might never understand why there is more matter than antimatter. We might never know what, if anything, existed before the Big Bang. The fundamental constants might have no deeper explanation, their values simply reflecting our location in a vast multiverse. The universe might retain some irreducible mystery, some questions that cannot be answered even in principle. As you rest tonight, consider that you live in a universe that remains largely mysterious, despite centuries of scientific progress. We have learned an enormous amount, tracing the universe's history from the first fraction of a second to the present, mapping its large-scale structure, discovering its fundamental particles and forces. Yet the most basic questions remain open. What is most of the universe made of? Why does the universe exist rather than nothing? Are we alone in the cosmos, or is our universe one of countless others? These mysteries are not failures of science, but invitations to discovery. Each unsolved problem represents an opportunity, a chance to learn something profound about the nature of reality. The universe is under no obligation to be easily understood or to reveal its secrets readily. That we have understood as much as we have is remarkable. That mysteries remain is what makes science exciting and meaningful. Dark matter and dark energy remind us that reality is stranger than we imagined, that the universe contains phenomena we have barely begun to understand. The matter-antimatter asymmetry shows that our very existence depends on processes we cannot yet explain. The possibility of a multiverse and questions about the universe's beginning push us to think deeply about the nature of existence itself, about why there is something rather than nothing, about whether our universe is unique or one of many. These questions may seem abstract, divorced from everyday life, yet they represent humanity at its best, reaching beyond immediate concerns to contemplate the deepest truths about existence. We are curious beings, driven to understand our origins, our place in the cosmos, the ultimate nature of reality. These mysteries inspire us to build ever more sensitive detectors, ever more powerful telescopes, ever more sophisticated theories, always pushing at the boundaries of knowledge. Perhaps within your lifetime, some of these mysteries will be solved. Perhaps we will discover dark matter's nature, understand dark energy's origin, explain the matter-antimatter asymmetry, find evidence for or against the multiverse. Or perhaps these puzzles will persist, remaining unsolved for generations, gradually yielding to incremental progress over decades or centuries. Either way, the search itself is valuable. In attempting to understand dark matter, we develop new technologies and new theoretical frameworks. In studying dark energy, we probe the deepest properties of space and time. In contemplating the multiverse, we refine our understanding of what science can and cannot tell us about reality. Every mystery, solved or unsolved, advances human knowledge and understanding. Sleep peacefully, knowing that the universe holds secrets yet to be discovered, that the deepest questions about existence remain open, inviting exploration and investigation. You live in a cosmos that is mostly mysterious, mostly unknown, yet gradually yielding its secrets to patient observation and careful reasoning. The universe that gave rise to you, that made you of stardust and consciousness, that placed you in this particular moment of cosmic history, retains profound mysteries, hints of deeper truths waiting to be discovered.